Hello again. It's the Diabolic Bee Tutor. We're back again with another situation. We're moving on to a tutorial for today. It's going to be with the rational functions. Some people call it rational functions, which might be confused with rational versus irrational. So the naming comes more from the idea that there's a ratio of sorts between thing number one, which is a polynomial, and then thing number two, which is also a polynomial. So I feel like the naming scheme for this one, rational functions, isn't that useful. I think polynomial ratios would be better as a categorization, but that's what some people decided, unfortunately. So let us get started with the rational expressions, or AKA, what did they say? Polynomial ratios. So when we're talking about ratios, we're talking about fractions. So we have fractions involving polynomial functions. So in other words, you're going to have... Whoa, that's very thin. Hold on. Oh, there you go. So we're going to have a fraction bar. There's going to be polynomial number 1, and then there's going to be polynomial number 2. And then you have their name and your functions. So f of x is equal to something like this. So again, if you recall, polynomial functions, they're just basically... they're basically things containing x's, and those x's have whole numbers, so no negative integers, so we don't have -1, for example. And again, they have to be whole numbers, so 1/2 ain't gonna cut it. So you have something like 2x to the power of 3 minus 5x plus 1 over, for example, 4x power 3 minus 2x squared plus x. So this one would qualify as a rational, what did I say? Rational function, yes. But again, in my opinion, the name should be polynomial ratios, but we're stuck with rational expressions. Too bad. Very unfortunate. And then when we're dealing with these ones, it's most of your rules involving polynomials will carry over, meaning you still need to know how to factorize. You still need to know how to set equal to 0 using and then solve for your polynomial using, what is that called? Zero product property. You're still going to have to do that. But now you need a little bit more. You need to know something called vertical asymptotes, horizontal asymptotes, which is just long-term end behavior. We already covered it in the polynomial section. And then like maybe a couple of other things, but ultimately a lot of stuff carries over, so you're not starting from square one, which is one of those nice things about the majority of math topics. You don't have just a sudden burst of random stuff like in other subjects. Case in point, biology, very infamous. You learn like one thing, like, oh, this section is going to be about biological macromolecules, and then boom, next section you're learning about something that hardly connects to it. Like, I don't know. Well, maybe somewhere down the line. Maybe not immediately, but like you might learn chemical evolution, or you might learn ambiogenesis, which is, I guess, related to biological macromolecules. But then after that section of early life on Earth, you're going to jump to, I don't know, photosynthesis or something, or evolution, which is kind of a far cry from biological macromolecules, depending on how your teacher teaches it. Anyway, going on a rant. Let's talk about rational expressions, aka polynomial ratios. And you're going to see three main situations. So we're going to have situation A. I'm just going to arbitrarily call it situation A, where you're given y is equal to, for example, you're going to have something like x power 1 minus 2, and then on the bottom you have x squared minus 2, for example. And I'm going to explain the differences between these scenarios, but first let me just list examples. So this is example number 1. And then we have another situation. Wait, why is my chat so messed up? Hold on. What? Oh. Hold up. Need chat to pop back up, just in case. Wait, why is it like this? Okay. It changed back to normal. Alright. Then we have scenario B. So something like this. And then you have something like situation C. And honestly, that would cover the majority of your situations in rational expressions, aka polynomial ratios. So what is situation A? Situation A is when you have your leading term on top, it's going to be off, it's going to differ from your denominator's leading term by 1 degree. So there's a 1 degree difference. So this one is one less than that one. So that's situation A. And then situation B, you have a leading term on top, leading term on bottom. They have the matching degrees. So it could be square on top, square on bottom, or it could be 21 on top and then 21 on bottom. It could be 8 on top, 8 on bottom. As long as these two are matching, I would consider that situation B. And then of course situation C, that's the only one left. It's when the degree for the leading term on top is 1 greater than the degree on the bottom. Okay. This one, I guess, has a little bit more scenarios. You could also have, you can have degree 1 on top, and then on the bottom you could have degree 3 as well. So this one, as long as the top one is greater than the bottom one, I'm sorry, as long as the bottom one is greater than the top one, the bottom degree for the leading term is greater than the top, the degree of the top leading term on top, then you have scenario A. This one, they have to exactly match. This one has to differ by exactly 1. Alright. So let me, you know what, I should probably write that down. Let me move this up here. And move this here. And then this one right there. Okay, so just to summarize the situation, it's when the degree on the top is greater than, I'm sorry, less than the degree on bottom. That's for the leading term. For the leading term. For the leading terms. And in here we have the degrees are the same. My goodness, my penmanship is atrocious. Are the same. And of course the last one, the degrees differ by 1. Should I write the whole thing? Degree of leading term in numerator. There's no space. So the degree of the leading term in the numerator is exactly 1 greater. Is exactly greater than the degree. I wish I could type on this. Of the leading term. Wow, there's a lot. I should have just left it succinct like this one, right? It's too late. I'm already committed. The leading term. You can't even see that. In the denominator, yes. In the denomos. Alright. That's basically your 3 scenarios. Again, the bottom degree is greater than the top degree for the leading terms. The degrees are equivalent for both leading terms. And then the degree on the top is greater than the degree of the bottom for the leading terms. By exactly 1. It has to be exactly by 1. Otherwise, you get a kind of a difficult situation that classes don't typically cover. All right. So let's just look at a scenario A. I'm going to leave this. I should probably leave. Yeah, leave it. Wait, there's no space. Oh, you know what? Let me shrink that. No, that's opposite. Slam that right there. So if we need to reference it, then we can reference it. Hopefully I won't delete it by accident. I probably will end up deleting it though. Alright. So let's talk about the scenario A. Again, where the degree on the bottom is greater than the degree on the top. Let's start with the simplest one first. So we have a y is equal to 1 over x. Very simple. This is going to be your most basic, or at least one of the most basic. I keep forgetting the name for this. What was it? Rational expression? Yeah, rational function. This is a rational function polynomial on top. It's just technically x power 0, and then x power 1 on the bottom. So here it is. I think there's another name for this. It might be called a reciprocal function or something. Yeah, I don't remember. I always there are a lot of names that I forget. But learn to recognize this. Again, the degree on top is 0, and the degree on the bottom is 1. 1 is greater than 0. So this qualifies for scenario A. Alright. So that's that. So what can we talk about when we're looking at this particular situation? Well, let's jump to the graphing first. Graphing window, I mean. So here's the graphing window. And there are a few things to talk about before we actually start graphing, so I should not put this up. Anyway, what do we have to talk about right here? So basically, there are values that you can put into this function. It's basically your number crunching machine. It's as if you go to a vending machine. There are numbers that you can put in, and then there are things that you can get out after you put things into your number crunching vending machine, right? So just for example, just imagine this, okay? So this is going to be the viewing window for your vending machine. This is like the open slot where you get stuff out, and then there's going to be some buttons to press on the side. So when we're referring to domains for functions, it's basically what can you input into your machine, okay? So from a certain point of view, if you put in money and you punch in the corresponding sequences, then you can get certain items from your vending machine, right? So let's say you want this particular brand of chips right here. It's like Flamin' Hot or something. We're not sponsored, unfortunately. Maybe it's like Flamin' Hot something. Oh, Flamin' Hot is copyrighted. Just kidding. Instead of Flaming Hot, Burning Hot. Yeah, that's close enough. Burning Hot Chippos. So you want some burning hot chipples, and that is located in A1. Okay, so basically there are a few things that need to happen. Unfortunately, this analogy isn't perfect because number one, you need to input money. It's probably $2 at this point. I don't know, 150. Let's say 150. And then you need to input the numbers. So I'm going to be talking about it from both perspective. You know what? Let's just keep it as A1. So basically there are burning hot chipples in A1 position. So you've already entered the money, and if you wish to get the burning hot chipples, you need to input the correct sequence. So you need to input A1. So that goes into your number crunching machine, your number vending machine, and once you enter those sequences, then the chips are supposed to pop out. The burning hot chipples, BHCs. That sounds like a chemical. I don't know. Burning hot chipples, right? So input and output. So there are things you can put into your machine. You can punch in the A1 sequence, and then there's something specific that you can get out. So this is referred to, you got to learn the words for this now. Some teachers are really emphatic on this. So this is called the domain, what your function can possibly take in. Let me put it right here. So the numbers that you press that are valid is referred to as the domain. So for instance, you can push in A1, you can push in A2, you can push in A3, but depending on the letters, you probably can't put X5 because X is not a valid number on this little dial pad, on this number pad. So as such, X5 is not within the domain of your number vending machine. So we can't put that. So understand that your domain is strictly what you can put into your function that is valid. And then of course there are things that you can get. There are specific things you can get from your number crunching vending machine. And there are things you sometimes cannot get. So in this example, you can't get soap or something, right? So you're looking for soap because you're stinky and you want some soap. So you go to this vending machine like, where's my soap? So you look in the vending machine and you, no matter what sequence you punch in, you could never get soap. Because, you know, vending machines don't typically sell soap unless it's, at least here, right? The vending machines I've been around in my lifetime, in my country, we don't have soap in our vending machines. So as a result, this one is not a valid output. So there is no sequence that you could input to get out soap. So the things that you can get out from your number crunching vending machine are referred to as something called your range. Your range of options. Your range of options are just chips for this one. And then maybe there's like some gum on the bottom and a candy bar or something like that. But that is basically the range of your function. So you have 9 different brands of chips, types of chips. That's part of your range. And then you have like a gum here, candy bar, and then candy bar. That's the entirety of your range of this number crunching vending machine. You can't get soap. Soap is not part of the range of options that you have access to. Again, domain is what you can dial in. You can just punch those. What are valid inputs? X5 is not valid. H5 is not valid. G might be valid depending on how expansive this thing is, but I don't think so. I think A, B, C's, and maybe D's at most for your number crunching machine. Plus a number, right? So D3 works, C2 works, B1 works, but G doesn't exist, so you cannot input that into your number crunching machine. So that's a short disclaimer of what we're talking about for domain and range. Again, domain and range are just the valid numbers that you can put into your function and the valid numbers you can get out of your function if you crunch numbers in your number crunching machine. So for example, look at this one. You can slam dunk a value of 2 into your number crunching machine. I want to change the name of this. So this one is the way that most people learn it in the beginning, but you learn to call it f of x, which is function name. This is your input. So this is your vending machine. This is the input you're putting into your vending machine. It does the work and then gives you a value. That's like the bag of burning hot Chippos that you can get from your vending machine. So if we put in a 2, for example, what happens? This is like the number you're punching in, right? So you're punching in 2. What happens when you punch in a 2? Well, this is what happens. 2 is the input for your function, and then the whirring of the machine. That one becomes therefore it becomes a 2. And what is 1 over 2? It's just 0.5, but I'll leave it as a fraction. It's 1/2. So if you input this, that's the number that you punched in, then that's the bag of 1/2 that pops out of the machine, and that's what you can munch on those ones. Perfect. So inputs, outputs, domain range. This is part of your domain because it's a valid thing that you can put into your function, and then this is a valid option you can get out of your function. All right. So let's just talk about this idea of domain and range a little bit more. It's not super, well actually it is kind of important because some teachers really emphasize this a lot. So is it possible to get a bag of 4, right? You want this as an output. Is this a valid output? So if you're curious about whether or not this is a valid output, all you need to do is just solve it mathematically. Is it possible to get an output? Well, we're hypothesizing that there's going to be some sort of A input. So this becomes A. If we input A into here, then that is the underworking of what's going on for the evaluation of the machine. So it becomes 1 over A is equal to 4. So can we solve for A? Yes. So you do the old switcheroo strat. So we divide both sides by 4, multiply both sides by a, so a is therefore 1/4. So yes, we can get a bag of 4. What do we need to do to get a bag of 4? We need to input 1/4. So just review that real quick. So if we plug in 1/4 into our function, then this one becomes 1/4. And then when you divide by 1/4, you do the goofy flip trick, so it's times 4. 1 times 4 is indeed a bag of 4. So yes, that is correct. So that's domain versus range. Again, domain is the things that you can dial in to put into your function, your inputs, and then your range are the values you can get out of your function, your bag of values. I hope that's clear. But again, no one's around to give any sort of feedback. So that's it for domain versus range. So can we put anything we wish into this number crunching machine? And the answer is no. There's one value that if you try to put it in, it will cause your function to break. It's as if you try to punch in z into your function. Or if we're talking about the coin input, if you're putting in money, for example, if you try to put in a wad of gum into the coin slot, then it will break your function. So what breaks this particular function? Well, you can put in any positive number you wish. You can try it out in your mind's eye. So for example, you can plug in positive 1. It will work because 1/1 is 1. So that's fine. You can plug in 100. So if you plug in 100, it becomes 1/100. That's also fine. So whole numbers seem fine. What if you plug in a fraction, 1/2? Well, we already saw what happened with 1/4. If you plug in 1/4, then you get 1/1/4, which is just goofy flip trick 4. So fractionals seem to be valid. Maybe what about negative values, right? Can we put in negative values? Can you put in -1, for example? Yes, you can. This becomes -1. So the whole thing is 1/-1, which is just -1. So negative seem valid. You can put in -1000, it'll be okay. And then the value you cannot put in is 0. Right here. Very specific. 0. Why can you not plug in 0? Why would... Because the short answer is, again, it will break your function. And the question is, why does it break your function? So let's see what happens. If your input is 0, then this part... If your input is 0, then this one becomes 0. And then if you try to divide by 0, it will fail. It will be undefined. So basically, it's as if you try to again, for your number vending machine, you try to put in Z5, but it can't find Z. It's undefined. You can't even find it. So therefore, this is the only thing that will cause your function to break. Okay? You can also plug in pi. Pi works just fine. It's just 1/pi. It'll be irrational, but it works. So the only thing that will not work for this particular type of function is 0, because you can't divide by 0. So this is a crucial thing. The failure of your function is if you somehow create division by 0. It will cause your function to fail, which leads us to the first idea of something called vertical asymptotes. It's just a fancy word. But it means that it's a graphical thing on your graph. Graphical thing on your graph. It's basically a wall on your graph that you cannot cross. And the reason why you can't cross it, your graph can't cross it, is because your graph has no value at that particular location. So, again, if you try to plug in 0 into your function, it will become undefined. Your function cannot take in that value. It will break your function. So what happens when it breaks your function? Let me write that down first. 1/1 is equal to undefined. So therefore, if you try to graph it, the rest of your graph exists, but right here specifically, at the x is equal to 0, there's something called a vertical asymptote. VA. For vertical asymptote, you spell it like this. Vertical, and then asymptote. Asymptote. And this particular asymptote is at x is equal to 0. So this is the definition of the wall that is the vertical asymptote. And it is a wall that your function f of x, this f of x, cannot cross. It cannot cross because it has no value there. You know how you have like a linear function? That one's straight all the way through. Well, for this graph, you're going to encounter this wall, and then you can't go past it. All right. That's the idea anyway. So what happens when so that's one idea you need to do. You need to have, and then you also need to know something called, you need to learn something called a horizontal asymptote. And we've already stumbled across that because horizontal asymptote is basically related to long-term end behaviors. So when your x values get absurdly large or when your x values get absurdly small, which should be a familiar phrase. So when x gets ridiculously large, what happens to your y values? So again, infinity is not a number, but for our brains, we can just pretend infinity is a very large value. Let's pretend it's a billion to the power of billion, right? Just to wrap our head around this idea of infinity. Which means that if we're trying to plug in a really large number, I'll represent that using infinity, but remember, infinity is not a number. So if you divide 1 by an absurdly huge number, it becomes almost 0, so approximately 0. So what happens as x keeps approaching, I shouldn't say keeps approaching. What happens when x becomes ever increasingly large? What's the trends for the y values? The y value trends towards 0. So that's what's happening. Because again, the bottom portion is becoming larger and larger and larger. You can do a number table to think about this idea. So if you plug in 1, for example, for your input, then the output is 1. That's not very big. If you plug in 10 into your function, 10, then you get 0.1. That's smaller than before, right? So, but if you plug in 1000 into your function, then you're going to get 0.001, which is even smaller. And this trend will continue. The larger the input that you put in, then the smaller the output you will get out. Which we can summarize using this statement. As x approaches positive infinity, then y values approach, or you could call that f of x. Then f of x, this is just synonymous with y, approaches 0. Alright? And of course we have the other directionality to care about. What happens when your x values are becoming smaller and smaller? In other words, a larger sized negative. Then we could say x approaches negative infinity. What happens there? So we're putting in a negative value that has a large size magnitude. Negative magnitude that's very large. Negative number with a magnitude that's very large. So you're putting in a super huge sized negative value. Then what happens? You're going to get approximately 0 yet again. But here's a minor thing to make note of. We don't write this for the symbol, but it's almost 0, but it's still negative though. It's a negative almost 0. But 0 is the criteria is the criterion by which you determine positive or negative. So most people wouldn't put a negative on the 0 because it doesn't make any sense. But I'm telling you, in dealing with these type of situations, for now we could consider this is almost 0. It's a negative almost 0. So we have f of x, which is just the y value, approaches 0, but it's almost negative. I mean, it's still negative. It's almost 0, but it's still negative. And the top one is still positive. It's a positive almost 0. And that's important because this in tandem helps us determine something called the horizontal asymptote. And the horizontal asymptote is just the long-term end behaviors of your functions. So if your x values are increasing, if you're plugging in larger and larger x values into this location, into this input, what is happening with your y values? Your y values are getting smaller and smaller. So if we do a table, if you plug in 1, for example, I should have deleted this. Oh no, it's too late. Well, let me delete this. Let's rewrite f of x. F of x is equal to 1 over x. Again, it's the same thing as this one. But this one is a little bit more informative because it lets us know the input explicitly. This one doesn't let us know the input explicitly. So this notation, we'll eventually discard this and won't use it as much. But this is the one that we will be focusing more on. So again, this one. If you plug in a 1 right there, then we get an output of 1. So you plug in 1, we get 1. That's nice. If you plug in 10, if you input 10, then this becomes 10 and this becomes 0.1, which is lower than what we had before. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We get 1/10. So there's kind of a decreasing in return. So the higher the x values that we pick, so if we pick this x value, we get this return. If we plug in this x value, we get a smaller y value than before. If we plug in this x value, we get an even smaller y value. So the values are decreasing. But it can never truly become 0. So no matter what number you put in the bottom here, even if you put 1 billion to the power of 1 billion to the power of 1 billion, you will never force this to actually be equal to 0. It'll be very close to 0. But what does even very close to 0 actually even mean? But don't worry about that. In other words, it's almost 0, but it's still a positive number. And that is basically why we draw this arrow very close to the x-axis, but we're still above it. So I put the arrow above like this. You don't cross the x-axis. Because if you cross the x-axis for this scenario, you're saying that we approach a 0 that is negative. But if you put in a huge value that's positive, you're still going to get a huge positive. You're going to get still a positive output. It's almost 0, but it's still positive. So that's why you don't dip below the x-axis. So in summary, arrow is above. And that's the trending pattern that is described in this particular statement. So again, when x values get larger and larger, y values get closer to 0, but they're still positive, which is this part. Okay. So if that's true for this side, if that's what's happening on the right-hand side, we can also summarize what's happening on the left-hand side visually. We can use this statement here, and we can create a visual on this side. So what is this saying again? As the x values are getting larger sized negatives. So we're going in this direction. So for example, you're plugging in -1. That's one value. You plug in a smaller value. That's -5. You plug in even smaller value, -10. Or even somewhere down the line, you're plugging in an even smaller number, -1000. What's the trending pattern in the y's as you are decreasing your x value inputs? You're going to be creeping closer to 0, but your output is still negative. Because again, if you plug in, for example, -10,000 or -100,000, you're going to get something very close to 0. But it's still negative. So almost 0, but negative. So hence, your arrow is going to be below your x-axis. Not above, below. Because it's still negative. So if you plug in a negative value that has a very large size, it's approximately 0. But it is not truly 0, so it still has a sign. The sign is still negative. Alright, and that's summarizing this part graphically right here. So if you plug in -1, for example, into your function, you get -1 as your output. So you're going to be right here-ish, and then all you need to do is connect this end behavior to this one. Smoothly as possible. Alright, so that basically summarizes something called the horizontal tangent. No, I'm sorry, not horizontal tangent. Horizontal asymptote. It's located at 0 because this one trending pattern is towards 0 on the right hand side, and then the trending pattern on the left hand side is also 0. So therefore, because these two trending patterns agree, we can say that the horizontal asymptote is y value, that's a flat horizontal line, is equal to 0. All right. So there it is. So we have an HA, again called the horizontal asymptote. And for this situation, it happens to be y is equal to 0, or f of x is equal to 0. All right. So that's so far so good. We're almost done graphing this thing right here. So we have this part of the graph. Again, make sure you understand that. That's because we have trending patterns. Again, as you plug in smaller values of x, then your overall y value approaches 0, but they're still negative. So you don't have, if your arrow goes down like this, you're implying that your y values are getting farther away from 0. The sizing is deviating from 0, but that will disagree with the patterns we're observing by actually plugging it in. So again, I hope that makes sense. But there's nobody to say otherwise. So unfortunately, we're just going to have to move on. All right. So magenta is the graph. But what's going on around this vertical asymptote, right? What does our graph look like? And to understand this one, you basically need to understand something called limit approach. But don't worry, you don't need to call it limit approach until you get to pre-calc or calculus. But for now, we're just talking about trending patterns. So again, if you plug in -1 for your x value, the y value is also -1. So the main situation is we can't plug in 0 into our function because it causes it to become 1 over 0, which is undefined, right? So we can't put in 0, but what if we put something very close to 0? So not quite 0, and definitely don't pick -1 because that already works. So we plug in something that is quote-unquote very close to 0 into your function. So what if we plug in something like, let's see, what can we plug in that's very close to 0? We can plug in 0. Ooh, that's bad color. We can plug in 0.0000001. Plug that in. So what happens when we plug in 0.0000001? Well, this whole thing here becomes 0.00001, which means if we divide 1 by this very small number, you get a very large number that's still positive. So very large positive value. You can imagine what keeps happening if you plug in an even smaller positive value, right? So what if we plug in this thing right here? And you plug that into your function. We're no longer plugging in this one. We're now plugging in this value. We're going to get an even larger output because 1 divided by super tiny number gives you a super huge number. That's positive. So that's the trending pattern. So if we try to plug in something very close to 0, our number output will explode in size. So let me repeat that. If you plug in a positive almost 0, so we're not plugging in +1, we're not plugging in 1/2, we're not plugging in 1/10, we're plugging in something very, very tiny. So what happens when you plug in something very small into here? Well, this part here becomes very small. And when you divide 1 by a small number, remember the goofy flip trick? Then the number value output gets very huge. Let me show that using fractions. So again, you could plug in 1 over 1 million. So according to goofy flip trick, this is equivalent to 1 times the bottom number, which is 1 million. So if you plug in 1 millionth, then the numbers explode, and you'll be like way, way past what I can show on this graph. But understand that it's way up there. So if you try to connect this one to this one as smoothly as possible, because there should be no other interruptions, because the only interruption we have is at 0. Any other value you can input into your function. You just can't plug in 0, because 0 causes division by 0. But anything else is valid. So that means that this graph from here to here should exist, and we got to connect it as smoothly as possible. So something like that. Let me get rid of the green stuff. that's the limit of my undo function. So let me manually delete that. So again, if you plug in a very, very tiny x value that's still positive, but it's very close to 0, it's to the right of 0, your number values explode. So you get something like this. You will never cross to the other side. Again, if you cross to the other side, you are implying that 0 is part of your domain. You're implying that your 0 works for this particular function. But it shouldn't, because you'll be dividing by 0, which is undefined. Alright, so that's what's happening on the right-hand side. But what if you plug in a value that's very close to 0, but it's negative? So we plugged in a 0, almost 0 that's positive. We get a positive huge number. But what happens when we plug in a very small-sized negative value, like negative 0.000000000, etc., 1? What if you plug in that? You could probably extrapolate that the same situation is going to happen, except it's going to be negative result. So if we plug in something 1 over negative 1 million, for example, so if you try to plug in negative 1 over 1 million, what happens? Then this part here becomes negative 1 over 1 million. So you're going to get 1, that's this one right here, divided by 1 over 1 million. So, which means you have to do the goofy flip trick. So 1 times, then you flip this around the reciprocal, times 1 million. And that's a huge size number, but it is negative because of the signage. Almost. Delete that. So just to reiterate, if you try to plug in a very small size negative value that's close to 0, it's not quite 0, then your y value explodes in size. So the magnitude is very large, but it's negative. So you get something like this. Now there you have it. That's the graph of your y is equal to 1 over x. So that's explaining it in the most detail that I can provide. So let's summarize that one real quick. Let's just go over what we talked about. We're talking about this particular function, 1 over x. That's going to be the situation A, where the degree of the bottom one is greater than the degree on top for both leading terms. We have to consider domain restrictions. What causes your function to break? In that case, that will be your vertical asymptote. Vertical asymptotes are walls that can't be crossed, because that would mean you're dividing by 0, and you can't divide by 0. And of course, there's long-term end behaviors for your function. What happens when your x values keep growing and growing and growing? Your y value trends towards 0, but it's almost 0, but it's still positive. So it's above your x-axis. And in the other direction, what happens when when x values trend towards very small size, I'm mixing my vocabulary. What happens when your x values trends towards smaller values, or large size negative values, right? Then you get close to 0, but they're still negative, which is why we're below the x-axis. And of course, we just talked about why this one explodes getting close to 0, and this one explodes getting close to 0. It's still negative though, because you're inputting negative values. Still positive because you're inputting positive almost zeros. And that's the graph of the function for y is equal to 1 over x. Hope that wasn't too bad. Alright, moving on. We got to talk about some other situations for this one. So let's look at another situation A type of problem. So still f of x is equal to, for example, let's do 1 over x minus 1. So what happens when we have a situation like this one? Well, let's do the analysis. Let's do vertical asymptote first, domain restrictions first. So we ask ourselves, What numbers can we not put into our function, into our f of x function, because it will cause our function to fail? Remember, when your function fails, if you have a fraction type function, it fails when you're trying to divide by 0. So in other words, when this bottom portion as a whole becomes 0. So how do you make the bottom portion into 0? You literally take the x minus 1, and then you set it equal to 0. Solve for x. So if x is equal to 1, then it will cause the denominator to be 0. Because again, 1 minus 1 is 0. If you try to divide by 0, it fails. Undefined. So what causes our function to fail? If x value is equal to 1. So x cannot be 1. So domain, x can't be equal to 1. Alright. What does that mean for us? It means because of this idea, we have a vertical asymptote. And the vertical asymptote is where it fails. Where does it fail? When x is equal to 1. So I know that seems kind of contradictory. We have a not equal to 1, and then we have an equal to 1. But remember, this is the wall that cannot be crossed. This is the value it cannot be. It cannot be 1. Okay, so that's for that one. And then, of course, long-term end behaviors. We need to talk about horizontal asymptotes. Do we have horizontal asymptotes? So evaluating horizontal asymptote without using any shortcuts or algorithms at the moment, we ask ourselves, what happens when this x value becomes a huge positive number? So check it out. So if x is an absurdly huge number, we'll represent that idea using infinity, but infinity is not a number. So if you have an absurdly huge number and you subtract 1, the whole thing is still an absurdly huge number. You know? So you're still dividing 1 by an absurdly huge number. Even if you've subtracted 1, it's still absurdly huge. So 1 divided by absurdly huge is approximately 0. But this is still a positive number, and that's still a positive number. So you put almost 0, but it's still positive. And you could probably infer what's going to happen if you try to plug in a negative value. So let's see. So what happens when we try to plug in an absurdly huge sized negative value? So you plug in something like negative infinity, which again, not a number, but we pretend it is for now. So you have absurdly huge sized negative value. You subtract 1, it's still going to be absurdly huge sized, but it'll be negative. Remember a while back I talked about the difference between size versus value. So this is a very small value, but the size is very large, but it's negative. Alright. So when you divide 1 by an absurdly huge number, it's almost 0, but it's a negative almost 0. So let's summarize exactly what we talked about. So as x approaches a huge size positive number, then the y value f of x approaches almost 0, but it's a positive almost 0. Most teachers, I don't think they want you to write this, but I'm going to write it. What happens when x approaches a negative large sized value? Then the y value f of x approaches almost 0, but it's a negative almost 0. And since right-hand trend agrees with left-hand trend, we could summarize this one. So the horizontal asymptote, the long-term behaviors. Why is it long-term behavior? Because we're talking about quote-unquote infinity approaches. So long-term behavior, both your y values in either direction approaches 0. So we have vertical asymptote, and then we have horizontal asymptote. Let's get to start graphing this junk. Alright. So here's the viewing window. Vertical asymptote, again, that's a solid wall that you can never pass. Or not a solid wall, that's an imaginary wall. Because again, you can't plug in 1. That will cause your function to fail. So as such, we put in these dashed lines to represent the invisible wall that cannot be crossed. And then long-term behaviors, when as x gets larger and larger positives, then the y values get smaller and smaller, but still positive. So we are above the x-axis, or y is equal to 0. Y is equal to 0 is the same as the x-axis. So we are above the x-axis. So right there. And then what's happening on this side again? As x approaches a large sized negative value, your y's approach 0. But they're still negative, which is why we are below the x-axis. So we have this trending pattern, long-term behavior, and we have this long-term trending pattern for the other side, and that summarizes the horizontal asymptote. So notice that both of these arrows are sandwiching the x-axis, or y is equal to 0. Alright. So we have our vertical asymptote there, and then we have our horizontal asymptote there. So all we need to do is finish the rest of the graph. Alright. So to evaluate what's happening, we can be very tedious about this situation. Again, we could use the same logic as before. We could say what happened. We can't plug in. Oh, I put the vertical asymptote in the wrong location. I put it at 0. So by drawing this one, I'm saying that the vertical asymptote is x is equal to 0, but we just established that it's 1. So I need to move this over. So the red dotted line is not there. So that's my mistake. Let me delete that. Let me rectify that. This is the y-axis. X can be equal to 0, because if you plug in 0, 1 over 0 minus 1 is a clean negative 1. So 0 is within the domain of your function. So your x values can be right there graphically. Graphically, we cannot have it right here at x is equal to 1. So this is where our imaginary wall is, the vertical asymptote. That's at x is equal to 1. Right there. Right there. Okay. So that was a correction. But let's go back to what we were talking about. How do you graph your function around this vertical asymptote location? You can't plug in 1 directly, but you can, in your mind's eye, you can plug in something very close to 1. And there are two numbers that are very close to 1. You can plug in something like 0.99999. It's less than 1, but it's very close to 1. Alternatively, you can also plug in 1.000001. This is not quite 1, but you can plug it in because you won't produce 0. So let's talk about each of those scenarios. And let me color code them real quick. Let's color code this one orange. This one, actually. So if you take this 0.99999 and you plug it into here, what happens? It's not exactly 1, because again, if you plug in 1, it fails. So we be a little cheeky about this and plug in something almost 1. So what happens when you have almost 1 minus 1? You get almost 0. But what kind of 0 do we get? Since this is smaller than 1, but it's almost 1, we get a 0, an almost 0, but it's still negative. I hope you understand that. So it's a little bit smaller than 1 minus 1 gets you almost 0, but it's still negative. But it's negative. So what happens when we divide 1 by almost 0? This is not truly 0, it's almost 0. We get a huge size number. We can represent that using infinity. So this infinity just means a very large size value, but it's negative right there. What does this mean? So if we plug in a value that's very close to 1 but is less than 1, then our y values begin to explode downwards. Because if you divide 1 by a negative value that's almost 0, your y value gets absurdly large. So that's why I'm representing it using negative infinity. This is, again, this is not truly 0, it's almost 0, which was what this negative means when I write it down. Okay, so all we need to do is connect this end behavior to this trend right here. So connecting those two together just like that. And that summarizes your graph on the left-hand side. What's happening on the right-hand side? We're going to do almost the exact same thing. So what happens when you plug in an almost 1 into right here? Because again, we can't plug in perfectly 1 because 1 minus 1 is 0. So again, we're being a little bit cheeky about this. Almost 1 plugged into here. But since this is bigger than 1, then slightly bigger than 1 minus 1 is almost 0. But it's still a positive number that is a little bit over 0. Okay, so the bottom portion becomes almost 0. So you have 1, you have this 1 on top divided by almost 0. But that 0 is almost 0, but it's still positive. So what happens when you divide 1 by almost 0? That's positive. Your numbers explode upwards like that. So all we need to do is connect this one to this end behavior as smoothly as possible. And we're done with the graph. Alright. So that is a very formal way of graphing it. It's not the most formal way, of course, because if we're using some crude idea of what limits are, but it's very robust in terms of graphing these type of scenarios. There's actually a much simpler strategy that you can use. And the strategy you can use is, after you determine the horizontal asymptotes, the long-term end behaviors, you could just plug in a number one space away from the vertical asymptote. Here's what I mean. So if the vertical asymptote is at 1, all you need to do is plug very close to 1 and plug in x is equal to 2. So what happens when x value is equal to 2? Check it out. What's 1 over 2 minus 1? It's just 1. Positive number, right? Which means for here, if you plug in 2, you get positive 1. Boom, there it is. And since you already know the long-term end behavior from before, you just connect this one to here. You don't know this one right here. But you go close to the wall, but then you creep up the wall. How do we know to creep up the wall? Because that's the trajectory of the graph. So you can see the y values in reverse are increasing. So you just follow that through. So that's the cheaty strategy. It's much simpler than evaluating limits. So how do you determine this part, again, without having to do this mindset of approaching 1? You plug in something very close to 1 on the other side, but you pick a whole number. You plug in 0. So what happens when you plug in 0 into here? We already did this one. It's 1 over negative 1, which is negative 1. So if we plug in 0 into our function, we get negative 1 here-ish. And connect that as smoothly as possible. So again, how do we know to go downwards and not go like upwards, for example? Because of the trajectory patterns, this one is slightly tilted. So we're going to follow through by continuing to tilt it downwards. And you never break past the wall, the invisible wall, because our x value can't be 1. Okay, so that's it. You have a number of tools at your disposal now. So let's go over a few more examples with scenario A, and then hopefully it becomes a lot more sensible. So let's look at something like f of x is equal to, let us look at, let's do a simple one first. 3 over x minus 1. No, let's do x plus 4. Something still relatively simple. Yeah, that's all we're going to do. So here's the viewing window for the graph. Okay, so first determine, we have a fractional situation with a polynomial on the bottom, so we ask ourselves what will break our function. We will break our function when the bottom as a whole is equal to 0. So we set x plus 4 is equal to 0, because we're trying to determine what will cause the bottom to become 0. So x is equal to negative 4. If x is negative 4, we create this 0, 3 divided by 0 scenario, which is undefined. So let's write that down. So x cannot be negative 4. That's the domain. Remember what domain is. Your valid inputs for x. So when we write something like this, we're saying that for the domain of this particular function, all values are okay to put into your function, into here, except for negative 4. There's a little more formal way to write this. You could write x such that x is not negative 4. And then you have these little squiggly brackets. You put domain as that one. So this is being super formal. I don't care for such formalities, but your teacher might. So that's it for the domain. Because the domain x cannot be negative 4, then we have a wall, a vertical asymptote, invisible wall, at the location x is equal to negative 4. So find negative 4. 1, 2, 3, 4. There's the wall. So VA, the vertical asymptote, and that asymptote is at x is equal to negative 4. So this is the wall that cannot be crossed. Long-term end behaviors. You could probably figure out the pattern by now, right? So if the bottom portion is x and the top portion has no x's, what happens when you make this a very large size positive value? Then you have 3 over huge value plus 4, which is going to approximate as almost 0, but it's still positive. So let's write the trending pattern. As x gets super large, then y value approaches almost 0, but it's still positive. Again, don't write this for your class. Maybe I should put it inside. Let's put it inside. Okay. Almost 0, but it's still positive. What happens when x approaches a large size negative value? Large size negative value plus 4 is still large size negative value. So 3 divided by absurdly huge is almost 0, but we have a negative value. So negative almost 0. So therefore, y value approaches 0, but it's negative. And since these two trend patterns are in agreement, we can summarize that using something called the horizontal asymptote. It's when the y values trend towards 0 on the left-hand side and on the right-hand side. Okay, so our graph is looking pretty good. You could probably figure out what the graph is going to look like. Honestly, when you do enough practice, you're like, oh, okay, this is going to be doing something like this. And since one starts below, it's probably going to be doing something like that. And that's going to be true for the majority of your problems, but let's not be too hasty just yet. So let's use the cheap strat. So this is negative 4. You can't plug in negative 4 into your function. So we plug in something very close to negative 4. Let me delete this real quick. There are some things I forget to undo. There it is. Okay. So again, we can't plug in negative 4 directly into our function, but we can plug in close to negative 4. So let's, again, we're using the cheapo strats, so we're not plugging in negative 4. We're not even plugging in something like negative 4.0001, even though this is very robust. So let us instead plug in negative 5 on the left-hand side, and then negative 3 on the right-hand side, because these are the easiest numbers you can plug in. You will see why. So if we plug in negative 5, that's one space away from our vertical asymptote. What happens? Negative 5 plus 4 is negative 1. Is that a coincidence? No, it's not. So 3 divided by negative 1 result is negative 3. So plugging in negative 5 will give us negative 3, which is what we predicted earlier. So that is done. What's happening on this side to connect to this end behavior? Plug in negative 3. So if this is negative 3, then negative 3 plus 4 is not coincidentally positive 1. So 3 divided by positive 1 gives us positive 3. So if we plug in negative 3, we get positive 3. So judging by this one, we're going to do something like this. That doesn't look good. There you go. And then that's basically the graph. As you see, we didn't have to do anything really fancy, but let me talk about that. So we're essentially done graphing this one, but let me just make a few comments. So again, if we're doing the more robust strat, basically we ask ourselves, okay, we can't plug in 4, but we can plug in something very close to 4. And there are two numbers that we can pick in your mind's eye. So you don't have to write it down. You don't have to write 4.00000001. So the idea is we're picking a number that's slightly bigger than 4. The negative 4, I mean. So negative 3.99999, for example. So if you plug in a value that's slightly bigger than negative 4, so this is negative 4, we're plugging in 3.9-ish, for example. So something here, what happens if we plug in that negative almost 4? Then the bottom becomes almost 0. But since the number we plugged in is slightly greater than negative 4, the 0 on the bottom is slightly positive. Okay, and when I say 0, I mean quote-unquote almost 0. So this almost 0 is still positive. So when you divide 3 by almost 0 positive, then your values explode upwards. So this is in agreement with what we've already done. All right. And of course, on the other side, that's plugging in something like negative 3.9-ish. That's very close to 4, but is slightly bigger than 4. What if we plug in something that is slightly less than 4, but is slightly less than negative 4, but is almost negative 4? Well, if you plug in something that's almost negative 4 here, like almost negative 4, then the bottom portion becomes almost 0. But because you plugged in something that's slightly smaller than negative 4, you're going to get something that's slightly negative. So it's almost 0, negative almost 0. So 3 divided by almost 0, that's still negative, explodes downwards. So we're still in agreement. So why not use the easier strat and just plug in numbers that are one space away from the vertical asymptotes, if they're available. Why not do that? But regardless, we're finished with this example. So let's do a slightly more complicated version, example of a type of situation A. Something like, I'll just write it down. Suppose we have f of x, and that is equal to 1 over x minus x plus 2 times x minus 2. So this situation, factor number 1, factor number 2, don't forget zero product property. So we ask ourselves, domain issues. Are there any domain issues? Yes. This one can become 0, and this one can also become 0. So there are two ways to break our function. Way number 1 is if x is equal to negative 2. Way number 2 is if x is equal to positive 2. So x can't be negative 2, and x can't be positive 2 for domain considerations. Which means we have two vertical asymptotes. So vertical asymptote number 1, what causes our function to fail if x is equal to negative 2? Vertical asymptote number 2, what's the other thing that will cause our function to fail if x is equal to positive 2? So we have two invisible walls when we graph. Long-term end behaviors. So if you multiply this junk out, let's do that real quick. So if you distribute the bottom, this is the difference of two squares if you recall. So x squared minus 4. So we ask ourselves, what happens when x becomes ridiculously large sized positive? So we get huge number, it's going to get squared. And then we're going to reduce that huge number, that absurdly huge number, reduce it by a measly 4, and we're dividing 1 by that result. So here's the idea. Huge number squared is still huge. Ridiculously huge number minus 4 is still ridiculously huge. So 1 divided by ridiculously huge is approximately 0 still. So nothing new there. But make note, everything on the bottom is positive, so this is a positive huge number. So we get a positive number that's almost 0. Let's check out the other scenario. What happens when x approaches? So this is when x approaches positive. Then y approaches almost 0. So what happens when x approaches negative huge size number? So let's see. Here's where things get a little dicey. X approaches a huge sized negative value. The whole thing is getting squared. Remember that. Minus 4. So when you have a negative huge sized number and it gets squared, it becomes positive. So absurdly huge positive number minus 4 is still absurdly huge and still positive. 1 is still on top. And like the previous situation, we're going to get almost 0, but it's still positive like before. And that's interesting because both of these are now positive. So in summary, because these are in agreement, we can say that there is a horizontal asymptote. And that horizontal asymptote is y is equal to 0. Alright. So we have the horizontal asymptotes and we have the vertical asymptotes. Let us populate the beginning of our graph. Okay, here is our viewing window. So we have vertical asymptote number 1 and negative 2. So 1, negative 2. We'll call that VA1. Again, that's at x is equal to negative 2. And then we have VA2 at positive 2. X is equal to positive 2. Remember, those are invisible walls. They will cause your function to fail. So we never cross those. This one, we have a horizontal asymptote by y is equal to 0. So it's still going to be right here-ish. Whoops. Oh no. Okay. So that's kind of a funky graph. And again, the long-term behavior is almost 0, but it's positive. So we are above the x-axis for this long-term end behavior. For this one, we are still above the x-axis because it's still positive. So don't put it right here. That's a negative almost 0. We don't have that because this squaring got rid of the negative value. So it's positive, which means positive almost 0. So we are above the x-axis. All right. So at this point, we have a couple of VAs, so we can just simply plug in x values that are one space away from those vertical asymptotes. And that'll be the easiest way to do these type of problems. So let us do that. So this is negative 2, so we're going to plug in negative 3. What happens when we plug in negative 3? Let's do it here. So remember, this is parentheses squared. So negative parentheses squared is positive 9. So 9 minus 4, it's 5. So you get 1/5. Positive 1/5. So plugging in negative 3 gives us positive 1/5. So we are above. So follow the trajectory. Don't just upturn it, downturn it like that. So following the trend, upturn trend, it's like this one. We can verify this using the more robust method. So let me show that robust method again. So we can't plug in negative 2, but we can plug in something very close to negative 2. So we can plug in something like negative 2.0001-ish. So it's very small. It's very close to negative 2, but it's slightly less than negative 2, okay? So that's the idea. We're plugging in something very close to negative 2. So the top part remains as 1. We're plugging in almost negative 2. So the bottom factor becomes 0. This factor becomes 0, but it's a negative almost 0. I'll represent it using this. So this number is negative. We don't care. It's still going to be a negative number because negative 2 minus negative 2 minus 2 is still a negative value. So what happens when you evaluate this? The two negative signs become positive. So 0 times a discrete value, almost 0 times discrete value gives you a very small value. So we have 1 divided by almost 0, that is positive, which means it explodes upwards. But we didn't really need to do that. But it's nice if you know how to do it. Alright. But we're using the cheapo strat. So what's happening here-ish? Well, we plug in a value that's close to negative 2, so we're going to plug in negative 1. So plugging in negative 1, most straightforward in here. You're going to get positive 1. Positive 1 minus 4 is negative 3, so we get negative 1/3 as a result. So if you plug in negative 1, you get negative 1/3, which is down here-ish. So what do we do with this one, right? Well, in this case, it's the more robust method is going to lead you to this idea. So I'll show you that real quick. Yet again, so we can't plug in negative 2. We'll plug in something very close to negative 2, but it's slightly larger in value than negative 2. So negative 1.999, for example. So let's see what happens. So if we plug in the number, the top remains 1. We plug in almost negative 2, but it's like negative 1.9-ish. So we get almost 0, but it's positive almost 0. This number here is going to be still negative. We don't care. So the two signs don't cancel. We still have a negative. So almost 0 times the number gets you almost 0 still. 1 on top. This one explodes. So we can pretend it's negative infinity. Again, infinity is not a number. So explodes downwards. And that is in agreement with what I'd said earlier. So it's going to explode downwards like that. All right. But if you don't like that strat, yet again, we have something called y-intercept, right? So in other words, wait, do we have a y-intercept? Yeah. Y-intercept is when you set your y value equal to 0. Is it possible? Oh wait, you know what? We don't have that situation. It's impossible. So if we try to find a y-intercept by setting the y value equal to 0, we don't have a solution. So we know we're not going to... Wait, that's weird. Did I goof something up? Let me ponder that for a moment. Oh, that's okay. We don't need it. We need... No, the y-intercept. I'm sorry. What am I saying? If we set y is equal to 0, that's the x-intercept. In order to find the y-intercept, we set the x value equal to 0. Yeah, there you go. So we set this equal to 0. So 1 over 0 minus 4 is negative 1/4. So if x value, not the y value, if the x value is 0, then the y value is negative 1/4, which is here-ish. So you can connect those as smoothly as possible. And from this trajectory, you can see that it aims downwards like that. But this agrees with our prior assessment. So you could probably infer what happens from here. It's probably going to do something like this. So, but let's plug in this actual point of 1. So if you plug in 1, or let's plug it here, right here. So we're still going to get 1 minus 4, which is negative 3. So we get negative 1/3. So if you plug in positive 1, you get negative 1/3. Let's connect those. Trust the trajectory. It's going to be shooting downwards like this. Again, we could verify this using the more robust approach, but we're not going to do it for now because we want to expedite the process. And then take a guess. Where do you think it's going to go? You have this to connect. Do you think it's going to be like this? No, it's not. Side note, this is actually parabolic nature. So this, it would be like this one if this had an even powered exponent. It should be very familiar. We literally talked about that in the previous video. If it's even powered, then it's parabolic in nature. If it's parabolic in nature, then you get down, down, or up, up. But we don't have that. So We don't have that exponent even that's 2. We have odd powered exponent, which is why we have, instead of this one, it's down up. I hope that's familiar. Okay, but let's pretend we don't have that. So all you need to do is plug in 1. We already figured it out. It's positive 1/3. And then you connect this trajectory as smoothly as possible. Trust in the trajectory for now. Just like that. And then we are good to go. Very nice. And thus, we have successfully graphed f of x part 3. I think that takes care of... Oh, we have one more situation for A-type scenario. Okay. So let us delete this part right here. Let us do the final example for the A-type scenario. So we have f of x is going to be equal to x minus 1. Now you see there's an actual x value on top rather than just having a constant. So we're going to have that over... I can't just put x minus 2 because this degree will match this one, which leads us to scenario B. So that's why I'm going to put an additional one. I'm just going to put x plus 2 yet again. Alright. Same analysis. We ask ourselves, what are the domain issues? Domain issues, how do we make 0 on the bottom if x is equal to positive 2? And if x is equal to negative 2. So they can't be those two values, otherwise you create 0 here or 0 there. So, which means we have vertical asymptotes at 2 locations. Vertical asymptotes are at x is equal to positive 2, x is equal to negative 2. I wrote that backwards. Whoops. Alright. And then long-term behaviors. We have x minus 1 on top, and then we have this multiplication thing on the bottom. So let me condense the bottom real quick. Again, there's a shortcut for doing this, but I'm not going to talk about it until scenario B. So distribute this one real quick. It's just a difference of 2 squares. This term cancels with that term on the distribution. So we get a difference of two squares. So x squared minus 4. So that's our function. As you see, exponent 1, exponent 2, so it qualifies as situation A. Alright. We are checking the horizontal asymptote, the long-term end behaviors. So first, we say what happens when x approaches huge values. What happens? Alright. This is where it gets a little dicey. Okay, because we now have a variable on the top and we have a variable on the bottom. But in terms of growth, constances are always outgrown. So this x value variable, as it gets larger and larger, will quote-unquote outgrow this negative 1. So the only thing we care about on the top in the numerator is just the x. And then, of course, on the bottom portion here, for sure, square functions outgrow constances, hands down. So the most important term on the bottom is just x squared. If you think about this, you can simplify this kind of, right? So this one is a huge number, and this is like that huge number squared. So you can do this crude simplification. Cancel x from top and bottom, you get 1 over x. So now we can evaluate this idea. What happens when x approaches, gets closer, I shouldn't say closer. What happens when x becomes larger and larger and larger? Then, this is a familiar situation, then the y value approaches almost 0. What kind of 0? Well, this is a positive huge number. This is also a positive huge number. So everything is still positive. So the 0 we are approaching is a positive. Let me rephrase that. We are approaching 0, but it is never 0. Because it's never 0, it still has a sign, and the sign is positive. There. Alright. And then we have to do it for the other side as well. What happens when x becomes a larger sized negative value, what happens? We're going to use this exact same strategy. So we're still going to approach 0 when this becomes exceedingly huge, but it's negative. Or, yeah. So we get a negative almost 0. So y value approaches 0, but it's still a negative value. So those two are in agreement. So therefore, we can say the horizontal asymptote as y is 0. That's nice. I'll just delete this. No, you know, I'm going to move it. So you shouldn't delete this work when you're doing your actual problems. All right, and then there's one more thing we can do that will help us with the graphing situation. Is taking advantage of this thing right here. We can finally set it equal to 0 in contrast to before. So we can find an actual x-intercept. So as a side note, you can't set the bottom equal to 0 because that would break your function, right? But we can set the whole function equal to 0, which means the top portion, how do we make 0? If x is positive 1. So set the top equal to 0, and that allows us to find the x-intercept. This causes the top value to be 0, so therefore x-intercept is 1, 0. And the reason why we want to find this is because it helps us graph a little better. Some teachers require this, but in my estimation, you don't really need this. So x-intercept. It's just extra filler for your work, in my opinion. Alright, so I think that's all we can do. We've already done the most. We've already set the top equal to 0. We've already set the bottom equal to 0 to break the function deliberately to find these two. We've done long-term end behaviors to figure out this one. So now we just get to graphing. Kind of buggy, so I need to clear that. Alright, let us get to graphing. We have the x-axis, wrong color. Alright, we have the x-axis, y-axis. Here's the viewing window. What do we have? We have the VAs at -2, +2. So let's mark that down. -1, -2. And then +1, +2. So VA1, that's at x is equal to -2. And then VA2, occurring at x is equal to +2. Horizontal asymptote at 0, y is equal to 0. Whoops, I'm going off of the... It has to be on the x-axis. So horizontal asymptote is at y is equal to 0 because it's a horizontal line. That's invisible. And don't forget this crucial, well, not crucial, I'm sorry. It's just slightly useful. We have an x-intercept at 1, 0, so right there. Alright. Cool. And that's the only x-intercept we should have. Okay, and again, using this idea, as x becomes larger and larger, y becomes almost 0, but it's still a positive number. So to the right-hand side, we are above the x-axis. And then as x approaches a large size negative value, y values approach 0, but it's a negative value, so we're under the x-axis, under the horizontal asymptote. And take a guess of what's going to be happening around these things. So it's probably like this, right? Well, what's happening in between? There's a certain symmetry. It's going to look something like this. I promise. Okay. But we're going to do the cheap strats by plugging in one space around the vertical asymptotes. So meaning we're going to plug in -3. If you plug in -3, what happens? We're going to get -4 over 9 minus 4, which is 5. So -4/5. So if you plug in -3, -4/5, which is like here-ish. So as promised, trust the trajectory. It's downwards like this. And now we plug in one space away in that direction from the vertical asymptote number 1. We plug in -1. So -1, you're going to get -2. You plug in -1. Squared is +1. So we get -1/3. Okay, I'm sorry, -2 over -3, which simplifies into positive 2/3. I'm sorry, positive 2/3. So plug in -1 will give you positive 2/3. So there's no trend to make note of, right? It's like, how do you know what's going to be happening? So this one, I'm actually going to use the more robust method, but we can use algorithms. So algorithms, you know what, let's use algorithms. So we have a vertical asymptote here at x is equal to -2. This one goes down, and this is going to go up. How do we know it goes up? Because the multiplicity, the multiplicity of this one is multiplicity 1, which is because it's multiplicity 1. If this one goes down, the other one goes up in opposition. But let's be a little more robust. So you can skip this part if you're on the VOD, but let's talk about this one. So the whole idea is if we plug in this -2 into here, it will fail, right? And we're interested in determining what's happening on this side. So we're going to plug in something that's almost -2, but is slightly bigger in value than -2. So something, for example, that's very close. That's like -1.999. That's the idea anyway. And let's just see what happens to the number trends. The top number will be a definitely clear negative value. This value here is close to -2 minus 2 is close to -4. So that's a definite value. But this one is almost 0. What kind of 0 is it? Well, something like -1.9 will get you positive output. So that is a positive almost 0. What does it mean for us? These two negative values will cancel out. So you have a positive number over almost 0, and that's 0. Almost 0 is still positive. So therefore, positive infinity, which means it explodes upwards, as we've already stated before. Okay. So regardless of what method you use to determine the directionality of this arrow, we can now connect this one to that x-intercept we found much earlier. So like that. Or like that. I think this is a little more accurate. Maybe. Let's do that. I don't want to commit myself. Let's do this. All right. So based off of this trajectory, it's not going to magically loop back up. It's going to go downwards like this one. Okay? So again, we could use this test. You could use this similar idea to figure out this one, which is, you know, let's not do it just yet. Instead, let us determine what's happening on this side of the graph. So we can't plug in +2, but we can plug in one space away, which is +3. So if we plug in +3, what happens? So we're going to get 2 over 5 2/5, positive 2/5, if we plug in 3. So if you plug in 3, we get positive 2/5. Trust in this. This one is higher than this one, so you have no choice but to connect it like that. Trust in the trajectory, so it's going to be going upwards. So since this one goes upwards, and this is, you know, +2 right here. This is degree 1, so multiplicity 1, so we have opposed arrows. So if that one goes upwards, then this one goes downwards. So this should connect to here. Something like that. And as promised, that's what the graph looks like. And we are done with this one. But I just want to talk about this one a little bit more to make it more robust. So let's use this. Whoa, that's too bad. Let's use this one. Okay. So why is it like this one, right? So the idea is, again, we can't plug in +2 because that's a vertical asymptote. It will cause our function to have a division by 0, which fails. So we plug in something very close to 2, something like 1.999. Smaller than 2, but almost 2. So if you plug in smaller than 2, but almost 2, this one becomes a positive value, clearly. If you plug in almost 2, we get close to 0, right? But it's slightly above. Wait, which one are we plugging in? Slightly below 2, okay. So we get 0, so we're plugging in 1.9-ish. So this is almost 0, but it's not 0, so it still has a negative sign. You plug in almost 2 here, that's a definite positive value. That's not close to 0. So when you evaluate this idea, the two positives, that's fine. Divided by almost 0, but it's negative. So which means it approaches negative infinity, which is why we can justify this downwards trend. So we already knew that from other methods. So we're done graphing this function, f of x. All right, and then I think that takes care of all the possible scenarios you would deal with for scenario A. Cool. Moving on to scenario B. Let me take some swig of tea. I hope it doesn't have too much caffeine. Otherwise, I'll be up all night. All right. Talking about situation B, right? It's going to be very similar. There are domain issues on the bottom. Well, there are still domain issues on the bottom. In fact, that's also true for C. Domain issues on the bottom, usually. X-intercepts on the top, right? Okay. So thankfully, scenario A, because I chose that arbitrarily in the beginning, it's like the most annoying to go to trudge to because there's just so much information to talk about. But now that we have scenario A as a basis, we can talk more easily about situation B. And that's when the degrees are matching perfectly for the leading terms. So no longer f of x, no, we're not talking about h of x. H of x is defined as, we have here on the top, x plus 1 over x minus 1. The leading term has a degree of 1, which matches the leading term on the bottom's degree of 1 as well. So this one qualifies for scenario B. So same analysis. We ask ourselves, what are the domain situations, domain problems we can get? Well, if the bottom equals to 0, how do we make the bottom 0? If x is equal to positive 1. This will cause your function to fail. So we can't have that. So in other words, x cannot be positive 1. Domain restriction. Which means that for the vertical asymptote, it exists and x equals 1. Because x can't be 1, then the vertical asymptote is x equals 1. All right. And now here's where things get a little more interesting. What's the long-term end behaviors, right? So what happens when x approaches positive infinity? It gets to become a larger and larger value. What's the trending pattern in your y values? H of x. Then h of x, what happens to h of x? Well, this is where it gets kind of funky, okay? We have positive x plus 1. We have positive x minus 1. So when this one becomes a huge size positive number, we get huge size number plus 1. You know, back in your elementary school days, infinity plus 1. You know, I'm greater than you infinity, and then the kid goes, I'm greater than you infinity plus 1, right? So here it is, it comes back. And then we have infinity minus 1. Again, infinity is not a number. I'm going to keep saying that over and over until you get tired of it. So how do we evaluate this situation? Well, in calculus, this is a bad situation. When you have infinity over infinity, it's kind of a bad situation. But we're not in calculus. We could kind of cheese the idea. So here is the idea. This infinity is so much greater than this 1. Okay, this huge value is so much greater than 1. So we can virtually ignore it. And then this number here is absurdly huge compared to this minus 1. So this subtraction of 1 hardly changes that huge number. So for sake of analysis, we can ignore those plus or minus 1. So we have, for all intents and purposes, a huge number on top that's virtually identical to the huge number on bottom. They're not exactly the same thing though, because this one is definitely increased by 1 and this one is decreased by 1. So in effect, this infinity is bigger than that infinity, but don't worry about that. So for now, just assume that x power 1 outgrows this constant. X power 1 also outgrows that constant. So in essence, this huge number is equivalent to that huge number, almost. So when you divide huge number that's practically the same as this one, you get 1. Which means this one approaches 1. Now here's where you need to be a little careful. This is my warning. So even though it approaches 1, it's not quite 1 though, because the numerator is plus 1 and then the denominator is minus 1. So in effect, the bottom number is slightly smaller than the top number. So we have a value that's slightly above 1. So be careful. Even though this is 1, I'm going to call it 1 plus. Alright. Don't write that for your class. Your teacher will very likely dock you off. But the idea is have this in your head. Or you just put a very tiny plus right here, like a very tiny 1 plus. I don't like that. I'll leave it like on the top. But this is the statement that you can write for your class. So what happens when x approaches? So the other end behavior, negative infinity, right? What happens when your x values? You're plugging in larger size negative values for your x. What happens? Same idea. Variables always outgrow constants, so we ignore constant number 1 on the top and constant number on the bottom. So in essence, we have same number divided by same number, which approximates as almost 1. But it's not quite 1. Okay? So if we have a very large sized negative value, right? It's a negative value. We increase it by 1. It's a slightly smaller size negative value than the bottom one. So the top one is a kind of negative infinity, right? And the bottom one is also kind of a negative infinity. But this negative infinity's size, because you have negative minus negative, gives you a bigger negative size. This negative is a tiny bit bigger than this upper large size negative. So even though the negative signs cancel out, you have almost the same number divided by itself, but the bottom number is slightly larger size than the top number. So you get something close to 1, but it's actually less than 1. So you have 1 minus. Okay. But since the two end behaviors match up, we could summarize it by saying the horizontal asymptote is therefore y equals positive 1. There it is. Wonderful. Let me delete the work right there. Let's take this and transfer it here-ish. Here-ish. So just to reiterate, you will write this for your class. You don't write this one and you don't write this one. But I'm trying to tell you that this 1 is slightly smaller than 1. And then that one is slightly bigger than 1. Because that will tell you whether or not you put your end behavior arrows above or below the horizontal asymptote. And I think some people just gloss over that, which is why some people get confused. Okay. And we do have an x-intercept right there. Or, yeah, we have an x. Wait, do we call it x-intercept? Yes, we have an x-intercept right here. So we can set x plus 1 is equal to 0 to find the x-intercept. Solving for x is equal to negative 1. So therefore, x-intercept is at negative 1 comma 0. So that helps us graph a little easier, but not much easier. The vertical asymptotes are more important than the horizontal asymptotes are more important. But why not have more pieces of the puzzle to make your graphing a little easier to do? All right. So we have the vertical asymptote, we have the horizontal asymptote, we have the x-intercept. So it feels very similar to scenario A, right? So here is the graph viewing window. Let me get rid of the scale thing. It's gone. So we have a vertical asymptote at x is equal to 1. There it is. So let's color that red. So that's a VA. And again, x is equal to positive 1. And now we have a horizontal asymptote, no longer at 0, no longer on the x-axis. It's at y is equal to positive 1. So right here for scaling purposes. So that's to contrast with the previous scenario. These ones, the horizontal asymptotes, are always 0. So let me write that down. Because the bottom leading term always outgrows the top one. So you're always going to get a 1 over infinity scenario, which is approximately 0. Versus this one, all the other terms can be ignored for analysis for the end behaviors. So as you see, it just becomes top number divided by bottom number. So if this had a coefficient of 2 over 1, then you just divide 2 by 1 for the shortcut to get horizontal asymptote y is equal to 2. But more on that later. In this situation, it's 1 over 1. So 1 divided by 1 is equal to 1. But again, more on that a little bit later. But this one, we found it more robustly through this particular method. So let us graph it. So here's where the slightly bigger than 1 and slightly lower than 1 comes into play. So as x approaches huge values that are positive, y values approach 1, but slightly bigger than 1. So this is exactly 1. We are slightly bigger than 1. For the other end behavior, as x approaches larger sized negative values, then the y values approach 1, but they're slightly below 1. Right there. Okay. And that is pretty good. You can probably infer what's going to happen for the rest of these stuff. It's going to look something like this. Because we have multiplicity 1. But for slightly more robustness, we're going to plug in values of one space away from this vertical asymptote. So we're going to plug in x is equal to 0, and we're going to plug in x is equal to positive 2, just to see what happens. So 0 first. If you plug in 0 here and 0 here as your input, then your output will be 1 over negative 1, which is negative 1. What just happened? Silly me. Whoops. Okay. So if you plug in 0, then we get negative 1. It's here-ish. So we need to connect this end behavior with this one right here as smoothly as possible. Unfortunately, this graph is kind of funky, but it should be doing something like this. I wish I'd drawn this a little better. But don't cross this wall. Never cross the vertical asymptotes. So something like this. Alright. I'm just going to cut it off. Let's not commit to anything. Alright. And then for the other side, we're plugging in positive 2. Positive 2 input. 2 here and 2 there. And we're going to get positive 3 over 1. Which is just positive 3. So it's up here-ish. So it'll be doing something like that. So connect this one to that one. You trust in the trajectory, so it goes upwards like that. And we are finished graphing this particular scenario. Again, where this exponent degree is in agreement with this one. Same degree. Everything else has been the exact same thing as with the scenario A situations. Oh, I forgot about this one. It's going to be negative 1, 0. Negative 1, 0. Here-ish. Not to scale, unfortunately. So good enough. So all things are present and accounted for, and behavior should be good. Vertical asymptote is good. X-intercept is there. So we have finished graphing h of x. First one right there. Okay. Not too bad, right? So let us move on to the next scenario B. Let's make things a little more complicated. So let us put, what do we do? Let's put this one squared, and then we'll put this one as squared as well. Because again, for scenario B, the leading term degrees must match up. 2 matches 2. Alright. So what happens in this scenario? We're going to do the exact same analysis. You're going to get so tired of this. What are the failures of the domain? What can we not put into the domain? This is a difference of 2 squares, right? So factorize, please. So x plus 1, x minus 1. Difference of 2 squares. This one is unfactorizable. We could use a discriminant test if you want to prove it. But in order to get rid of this plus 1, you need a negative 1. But you can never get negative 1 from squaring real numbers. So top portion is unfactorizable. Well, at least with real coefficients, right? So this is what we have when we factor h of x. So let's figure out what breaks our function. So breakpoint number 1 if x is equal to negative 1. So x can't be negative 1 because you will create 0 here. Breakpoint number 2 if x is equal to positive 1. Can't be positive 1. So those are domain restrictions. Because we now know those restrictions, we can write the vertical, not horizontal, vertical asymptotes. So we have VA1, which is x is equal to negative 1. And then we have VA2, x is equal to positive 1. So done and done. Long-term end behaviors, horizontal asymptotes essentially. What happens? Well, do the analysis again. On top we have x power 2, which will outgrow this constant for sure, so we pretend this doesn't exist. Exponent 2 outgrows constant, so pretend that doesn't exist. So in essence we have x power 2 over x power 2, which simplifies into 1. And that is the horizontal asymptote. That's the shortcut. That's the algorithm. Whatever if this had been coefficient 2 and this had been coefficient 3, same analysis. This term outgrows that term, so we ignore this. In essence, and then this one on the bottom outgrows this constant minus 1, so we ignore that one. So in essence, we have this almost the same number here divided by almost the same number there. So these ones in essence cancel out, thereby leaving us with 2/3 as an approximation for end behaviors. But it's not 2/3, it's 1 over 1. But let's be complete, let's write that down. So as x approaches a huge number, then your y value approaches what again? Ignore, simplify into 1. So approaches 1. Same thing for the negative. So as x approaches negative infinity, what happens for the situation? Same idea. We have here, ignore that. Anything divided by itself except for 0 is approximately 1. I mean, is 1. But this one that we're doing is approximately 1. And now we do the careful considerations. Remember. Even though this is quote-unquote infinity squared plus 1, it's slightly bigger than infinity squared minus 1. So for the top approach, as x approaches positive infinity, we are slightly above 1. So it's going to be 1 plus. What about the negative approach, right? Now here's where things get kind of dicey again. So this is negative huge number, right? But when you square a negative huge number, it's positive. So this is a positive huge number, and this one here becomes also a positive huge number. At this point, this positive huge number is the same thing as this positive huge number. But once you plus 1 and you minus 1 respectively, then the numerator is slightly bigger than the denominator. So it's not exactly 1, it's almost 1. It's a little bit bigger than 1, so I'll put 1 plus. Which is pretty important when you get to graphing, when you decide whether you're above or below the horizontal asymptotes. Alright. Again, since these two are in agreement, then we could summarize that the horizontal asymptote is y value equals 1. Do we have any x-intercepts? No, we don't. But we do have a y-intercept. If we plug in 0, 0 right here, our y-intercept, we might as well write that down. So if we plug in 0 here and 0 there, then our y, oh, that's too green. Then our y-intercept is, what is it again? 0, comma, negative 1, yes. Negative 1. Again, this just helps us with graphing just a little bit. It's not totally necessary. Get to graphing now. X-axis, y-axis. Since our horizontal asymptote is at y is equal to 1, I'm going to draw the graph a little. I'll put this bar a little lower than typical. Alright. Let's take care of the vertical asymptote plots first. Negative 1, positive 1, yes. So here's negative 1. Here's positive 1. VA1, VA2. X is equal to negative 1. X is equal to negative, positive 1, I mean. Alright, takes care of the two vertical asymptotes, and then we have the horizontal asymptote. It's at positive 1 for y. And here's where the slightly bigger than 1 comes into play, right? So for both end behaviors, we are slightly bigger than 1. So we approach 1. The y values approach 1 as x values get larger and larger, but we're still above 1. And as the x values approach large size negative values, we approach 1, but we are still above 1. Because we already analyzed that. Alright, so what gives about the rest of this stuff? Oh, let's put the y-intercept. 0, negative 1. Here-ish. Again, you could probably have a good idea of how this is going to happen, how this is going to play out. It's probably something like this. There's a certain symmetry that's very nice. So this one is kind of symmetrical, right? This side here is almost a mirror image of this one. So as a quick note, if you have, this is talking about other graphs, okay? So if we have something like this and something like that, then this inner portion part might be something like this. Again, depending on multiplicities. So there's a nice symmetry that you will eventually get used to figuring out. And you figure those out by doing enough problems. You will have ingrained in your brain what these things will look like, and it'll become a lot faster. Right now I'm just going fairly slowly because I want to cover as much as possible. Alright. So we've already plotted the vertical asymptotes. We've already plotted the horizontal asymptote with the arrows above and above. We've plotted the y-intercept. So now we just need to plug in one space away from the vertical asymptotes. So plug in negative 2, for example. So negative 2 in parentheses squared, negative 2 in parentheses squared. So we have positive output. Positive output. So trust in the trajectory and go up. All right, and let's do this one. I'm kind of going out of order, but there's no real order, so to speak. So let's plug in positive 2. Same situation, 2 squared, 2 squared. So 4 plus 1 over 4 minus 1. It's a positive number above 1. So we're there-ish. We're there-ish. Trust in the trajectory. There it is. So as promised, we have this one and we have this one. So we could probably figure out, because these are multiplicity 1 and 1, we have alternation going up, alternates with going down. Alternation up goes with down. So something like this. Okay, but if you're trying to use the plug-in strat, we can't plug in one space away from the vertical asymptote because we already have that right here. So you can plug in 1/2. So if you can't plug in exactly one space away from the vertical asymptote, just plug in half space away. It's not the nicest though. So let's see. So we have 1/2 squared, 1/2 squared. So plus 1 is positive on the top. 1/2 squared is 1/4. 1/4 minus 1 is negative. So this top portion here becomes positive number, and the bottom portion here becomes negative number. So that means we are below the x-axis, which agrees with what we said before. You can plug in 1/2. Oh, I plugged in positive. Whoops. So plug in positive 1/2 gives you negative something down there. Here-ish. So if we plug in negative 1/2, it's going to do the same thing because it's in parentheses. So we can recycle the work we just did before. So same output as plugging in positive 1/2. So something like here-ish. So connect, trust in the trajectory, trust in trajectory. And we're finished graphing it. H of x, that's going to be the situation. It's not too bad, as you can see. But we're essentially done graphing this situation, but I do want to talk about just doing the robustness for this one and this one again. Alright, let me talk about that again real quick. So we can't plug in positive 1 exactly, but we can plug in slightly less than positive 1, right? See what happens. So if we plug in slightly less than 1 plus 1, it's still a positive number up on top. If you plug in something slightly less than 1 plus 1, it's still positive for that factor. But if you plug in slightly less than 1 minus 1, you get almost 0. But what kind of almost 0 do we have? Because it's slightly less than 1. So this whole thing is still negative. It's almost a negative 1. So when you simplify this idea, it's like a positive divided by almost negative 0. So you get negative infinity. So it explodes downwards. Same analysis will show you it explodes downwards there as well. Which means we've finished talking about h of x completely for this current scenario. So let us clear that. So we're going to do a little bit more scenarios with scenario B. As promised, it was very similar to A. A gives us very strong basis for scenario B types. Alright. So far for these scenario B types, we've had only like one variable on the top. So now let's do multiple variables on the top. Multiple terms, I mean. So let's do x squared minus 3x plus 2 on top. And then x squared, let me think, minus, I want to pick nice numbers, is why I'm hesitating right now. Minus 1x minus 3 times 4. No, let's do 4 times 5 is 20. Yeah. Alright, so this is going to be our h of x. So a lot more complicated looking, but I promise, exact same steps as before. So you can factorize the top and you can factorize the bottom, but let us first analyze the bottom part. So we can find domain restrictions, so we can find vertical asymptotes. So the top one factorizes into x, same signs, same both negative. So 2, and then x minus 1. Alright. So we have a couple of x-intercepts. Bottom portion factorizes into x minus 5x plus 4. Okay. Let me double check. Yes. So let us begin by finding the domain restrictions. So x equals 5 cannot be 5. X cannot be negative 4. Those are domain restrictions, which means we have two vertical asymptotes. So vertical asymptote number 1 is at x is equal to 4. Negative 4, I mean. And then vertical asymptote number 2. This is all arbitrary. It doesn't matter which one you call which one. X is equal to positive 5. Alright. I know I kind of swapped the order, but like I said, it's not important. It's just for naming sake. Alright. Now let's do the long-term end behaviors. So this one looks a lot more complicated, but don't worry, same ideas. Constances never change, so those two terms will outgrow this one. So you pretend this one doesn't exist. Those two will outgrow negative 20, so we pretend that doesn't exist. So we're just looking here for now, but you can go a little farther. The large numbers, when we're talking about exceedingly large values, x power 2 outgrows x power 1. So we also ignore this one, and we also ignore that one. So for all intents and purposes, we are only paying attention to that one. So in essence, this top number here is practically the same thing as this bottom number here. So any number divided by itself, because we ignored those ones, is approximately 1. So therefore, as x approaches a huge positive number, these ones we can virtually ignore. Which means that the y value, h of x, is going to approach what? Basically, again, these ones are ignored, so we only have these ones left over. So huge numbers squared over almost the same huge number squared will get you 1. But will it be slightly bigger than 1 or slightly below 1? And that is a delicious question, right? And that's where the rest of these numbers come in. So these ones aren't so important because now we have this other important one to pay attention to. Because in consideration of whether or not it's slightly above 1 or slightly below 1, look what's happening here and here. We're taking away 3 times this huge number versus negative 1 times the huge number. Alright, since this is a positive value and we're taking away, this top number is actually a little smaller than this bottom number. So this 1 is actually slightly below 1. So I'll put 1 minus. Alright. Now, moving on to the other end behavior as x approaches negative infinity. What happens to the y values? Same thing, same logic as before. These ones are definitely outgrown. We essentially only have huge negative squared over huge negative squared, which approximates as 1. But the question is slightly bigger than 1 or slightly below negative 1. So same analysis, but now we have to deal with negatives. So if you have negative times huge negative, it's actually plus huge number now. So the top portion is slightly bigger than this one. Because again, we're putting a large size negative value. It's 3 times that. This is only 1 times that. So this top one is slightly larger than the bottom one. So this is slightly bigger than 1. So we have 1 plus. That's probably like the most complicated thing for the scenario. Most people stop just by using the algorithm. So if you don't like thinking about this too much, just think about, you can use a shortcut. Pay attention to the largest term on top, largest term on bottom, divide the coefficients. 1 divided by 1 is 1, and that's your HA. Y is equal to 1. Most people just do it that quickly and they stop there. But the problem is, again, they don't know whether to put the arrow above or below the 1, depending on some scenarios. It becomes a little tricky. All right. And again, we do have some, what are those called? X-intercepts, right? So we should solve for those ones. X-intercept number 1, if x is equal to positive 2. X-intercept number 2, x is equal to positive 1. So 2 x-intercepts, which may or may not help us too much. Flips. So x-intercepts, we have 2 of them, 1 comma 0 and 2 comma 0. You have to put 2 numbers because that's x, y coordinates. Don't just put 1 number, okay? So if you, for example, this is being a little pedantic. So if you say x-intercepts are 1 comma 2, this is technically wrong because x-intercept is on the Cartesian xy plane, so you need 2 numbers. So you need to put it like this, point, xy coordinate point, rather than just a single number. Some teachers are kind of picky and others don't really care. All right. I think, oh no, we need to find y-intercept as well. Let's do y-intercept. So this is 0, 0, 0, 0. So we have 2 over negative 20, which is negative 1/10. So if x is 0, y is negative 1/10. And that will be our y-intercept. So we have the 4 major things to talk about. We can now begin to populate our graph. X-axis, I'm going to put it slightly lower. Alright. Let's deal with the vertical asymptotes. That's my order of operations. You can start upwards, downwards, or downwards, upwards. It doesn't matter. So we have negative 4. Well, let's put it right here-ish. And then we have positive 5-ish. So this is VA1. And x is equal to negative 4. That is VA2. X is equal to positive 5. Alright. Oh, if I write the horizontal asymptote, since these are both in agreement, then the horizontal asymptote is y is equal to positive 1. So find positive 1. Let me think. 1. So it's about this far. So here-ish. There we go. Horizontal asymptotes are taken care of. Let's do x-intercepts at 1 and 2. Oh, that's going to be funny. Where are we? This is 1, 2, 3, 4, 5. So at 1 and 2. So at 1 and 2. And then lastly, we have the y-intercept. So we have 0 and negative 1/10. So here-ish. Alright. Are we missing anything? Oh, I'm sorry, the arrows for the end behaviors. Alright. So for the x approaches positive infinity, that's the right-hand situation arrow. We're slightly below 1. So there-ish. And then for this situation, we are slightly above 1. So we're there-ish. All right. And I think we're good to go with the plug and jugs. So let's do plug and jugs at this point. All right. So let's plug in one space away from the vertical asymptote number 1. So we're plugging in -5 here and -3 there. So what happens when we plug in -5? Well, that's annoying. That's annoying. Well, if you plug in -5, that's... should I do it fully? Yeah, okay, that's fine. This is going to be positive 25. That's going to be positive 15. That's positive. So we have a positive number. I should write it out. And then we plug in -5 in here. -5 in there. That comes 25 plus 5 minus 20. So everything is still positive. So we're going to get positive 10 on the bottom. And then we're going to get 42 on the top. So that's like 4-ish. So we plug in -5. It's 4-ish. So here-ish. Trust in the trajectory. It's going to be going like this. All right. So that takes care of the first plug and jug. And again, because this is at this particular factor, this is multiplicity 1. So this one goes up. We have an opposing arrow going downwards because again, it's odd exponent. So like this. But you know, we could always plug in. We could always do plug and jug. So let's plug in something that's one space away from -4, which is -3. So plugging in -3, we get positive 9, positive 9, 2, positive 9, positive 3, -20. The top number is positive 20. The bottom number is a negative value. It's like -8, right? Yeah, -8. So that's like -2-ish, like -2 point something. -2 point something. So if we plug in -3, that's -2 point something. So down here, as promised, we've already established that these will be opposed. All right. So this is a little funny, right? So do we do this? And then like what? Like that? Or do we do something like this? So this is especially dubious. Okay, we definitely can't be like here-ish. We definitely cannot. So it's gonna be like, so nothing like this. We can't do this. Absolutely not. Alright, I was just texting a friend. Okay, so like I said, what goes on between here and here, right? Do we try to connect this as smoothly as possible? And then here, what do we do from here? We can't go straight across to this one because that implies multiple zeros. So I think it's going to be something like this. It looks a little bumpy. It doesn't look super smooth because this is hand-drawn. But that's probably it. Okay. But we'll do a little bit more tests. Alright. What are we doing? We are doing more test points. So we're trying to figure. We already plugged into the left of this vertical asymptote and to the right of this vertical asymptote. So let's do the same thing for vertical asymptote number 2. So plug in one space to the left and one space to the right. So +4 and +6. So let's do +4 first. So 4 squared is 16. Minus 12 plus 2. So that's +6. And then we're plugging in 4. So we get 16 minus 4 minus 20. So that's a negative value in the bottom. Yes. So that's -8. So that's like almost -1. Almost -1. So plugging in +4, we get we get -3/4. So this one connects to this one. Trust in the trajectory. It goes down. This one connects to this one. It's this one. Again, it looks kind of funky. Like, what's this weird bumpiness? But it's only because This is hand drawn. So let me delete this. And we'll try to beautify it, okay? Something like that. That's the best I can do. Alright. And this is where, what the heck is going on right here, right? Why is this below the horizontal asymptote? Is it going to be doing something like this? No, it's multiplicity 1. So we don't have this parabolic down-down situation, so no. So is it going to be something like that? Well, let's plug in positive 6. So we can delete this work now. So plug in positive 6, we get 36 minus 18 plus 2. So 36 minus 6 minus 20. Alright. So what is going on? We have 18 plus 20 plus 2, which is equal to 20. And then we have 30 minus 20, which is 10. So we get positive 2. So plug in positive 6, we get positive 2. So it is, in fact, yes, going upwards like this. But wait a minute. Can we do this? Can we cross the horizontal asymptote? Isn't that breaking the invisible wall? Yes, we can cross it. Because horizontal asymptotes just describe long-term end behaviors, not localized small-term close to like discrete values like 5, 6, or 4. So this is actually okay. This is just localized behavior. But horizontal asymptote is just describing long-term behaviors because we're talking about exceedingly huge values. So it is okay to cross horizontal asymptotes. But you can never, ever cross vertical asymptotes because you can never divide by 0. If you try to divide by 0, it will break your function. Okay. So that's basically that. So again, I think by my estimations, most people who don't bother with this analysis right here, they would put it above, and then they'll put it above, which is wrong. It's supposed to be below. All right. If you are not convinced, we can plug in a very huge value, right? As long as we plug in an x value that's past this one, we should dip below 1. So I want you to see this. So picking a value, let's pick 1,000, right? Just to plug in to check out the end behavior, right? So if you plug in 1,000, we're going to get 6 zeros. So 1, 2, 3, 1, 2, 3. So 1 million on the top minus 3,000 plus 2. And what's happening on the bottom here, we're going to get 1 million again minus 1,000 minus 20. As I promised, this one subtracts more from this than does this one subtract from that one. So subsequently, the top numerator, the numerator is going to be slightly less than the denominator. Because these two pale in comparison to this huge quantity, so we can ignore this one. So we have big number minus 3,000, the same big number minus 1,000. So the top one is more reduced than the bottom one. So we get close to 1, but it is below. I mean, it is, how do you write that? It is below 1. Yes. Which is why we are below the horizontal asymptote. So again, if you don't do this analysis and you just do the shortcut where you go, oh, okay, the horizontal asymptote is therefore y is equal to 1, it most likely leads to putting this one on top and that one on top, which is technically wrong. And depending on your teacher, they may or may not deduct you points for that one. But let's try to be as complete as possible. We put this underneath the horizontal asymptote. So let me put that explicitly. Okay. And that's basically it for this particular graph. I think we've exhausted most of the situations. Oh, unless we have a repeated, let's do a repeated situation for h of x. All right, and that'll be the last one for scenario B. Okay. So we're still talking about scenario B, but let us talk about the bottom, the weird situation in the bottom. What if you have x minus 2 on the bottom, but that is squared, multiplicity 2 now, right? And then the top portion is just going to be x squared plus 1. So this is non-factorizable. This is fully factored already. So same analysis as before. How do we break the bottom? There's only one way to break the bottom if x is equal to positive 2. So therefore, for domain purposes, x cannot be 2. Therefore, vertical asymptote is x is equal to 2. All right. So that's the vertical asymptote analysis. Let us do the horizontal asymptote analysis. But first, let's expand this. So we're going to get x squared plus 1 over, I hope you remember your algorithm, square the first one. First times second times 2. So negative 4x. And then this one squared is positive 4. All right. So you can use the shortcut algorithm. You know what? Let me change the problem just a little bit, because there's something I want to emphasize. So let's say this had been a 2 and this had been a 3. Okay, so I'm just changing the problem. It doesn't change very much though. All right, I just want to specify that, which means this bottom portion is going to change. Okay, so same algorithm. We're going to get x squared times 3. That's going to be this one times negative 2 times 2, which is negative 4, times 3 is negative 12. And then negative 2 squared is positive 4 times 3, which is 12. All right. So it doesn't change the vertical asymptote because putting 2 into there still breaks the function, so we're good. All right. Because I want to make a different horizontal asymptote. All right. So long-term end behaviors. So same analysis as before. You can't ignore all the other terms. Just find the highest degrees possible for the shortcut. So this is the shortcut. Take the coefficient number 1, divide by coefficient number 2. So 2/3. So that's why you can get your horizontal asymptote very quickly. And this strategy works for scenario A as well. So scenario A, where's the x squared on top? Well, there is an x squared on top. It's plus 0x squared. So when you acknowledge that, it's going to be 0 coefficient divided by 1 coefficient, which is why horizontal asymptote is always y is equal to 0 for scenario A. That's a side note. So that's a shortcut. But again, it doesn't tell us for the end behaviors whether or not we are above 2/3 or below 2/3. So if you stop here, you might be missing some key information. So let us evaluate. Okay. What do we have here? Well, okay. What do you think? If x approaches a huge positive number, what happens overall? So this is a huge positive number, this is a huge positive number, and this is a huge positive number as well. The constances we can pretty much ignore since they don't really affect, well, they do affect, but very marginally do they affect exceedingly huge values because we have this other x term in the bottom. So what happens here? Well, we have, oh, this is actually a little more difficult. Let me think about this. Because we do have a confounding times 2 on the top and then a 3 on the bottom, right? I'm actually not sure. Does the 2 and the 3 matter in the front? Yes, they do, because that leads to this idea, right? Okay, I am going to say that because this is getting multiplied by 3, this is pretty much, we can ignore it as well. Okay, if this number 3 on the bottom was 2, or this one was 3, for example, then I would say that this one becomes an important player. But because this is 3 on the bottom, which is greater than the... I feel that's not good enough. Let me think. Let me think. Okay. Let me cheat a little bit and go use some limits real quick. Hold on, let me see something. Wait, can I? Let me think. So this is the problem when you don't have that, your mathematics isn't that good. I'm not a real mathematician, unfortunately. So this one, what happens here? If x approaches positive infinity, will we get above 2/3 or below 2/3? We could do a simple test by just plugging a huge value just to see what happens, right? But I feel we can do better than that. Yeah. To not get bogged, let me think. Should I? Well, let's see. Well, the most we can do is we can ignore this one, right? And we can ignore this one. Okay. Because this is actually tough. Let me think. Let me see the 2x squared plus 1 over that junk. So it's a good thing I changed the coefficients, because now we're bringing up a weird scenario, right? Okay, we can multiply top and bottom by 1 over x squared. I don't think this helps. Does it? Let me see. Again, don't worry about this. You could, if you're watching this on the VOD, just ignore this. We'll skip over this. All over what? 3, and then minus 12 over x plus 12 over x squared. So what happens when the x values are exceedingly large? This is approximately 0, but we're still adding to 2. This one is still subtracting from. This is super tiny, so this is more important than that one. So we're subtracting from the 3. So the 3 is reduced and then the 2 is increased. So the result is slightly bigger than 2/3. Okay, there you go. Yes. So the limit approach is a little better. All right. So now we'll come back to this situation. So how can we explain that without using limits? Let me think about this. Okay, so understanding this one, ignoring the other terms, we get 2/3. If it was exactly this one, and x approaches a big value, then this one perfectly cancels with that one, right? But the idea is we are deviating from 2/3 by increasing the top by a little bit. So this top 2 is slightly bigger than 2, so it's going to be 2 plus. And then this one is slightly reduced. The 3 is slightly reduced by this huge thing right here. This is ignored because this one is bigger, subtractive than this. I'm sorry. This one contributes more of a change than does this one. The plus 12 is marginal compared to this one. So this minus 12x is actually reducing that 3 thing in the end. So this is actually less than 3. So when your denominator is slightly less than your numerator, then this whole thing is slightly bigger than 2/3. Yes. Okay. So as x approaches positive infinity, then y approaches slightly more than 2/3. I'll put 2/3 plus. All right. And we can imagine the opposite thing is happening, but let's verify that real quick. So if we have x here approaching a large size negative, then again, these ones are the major players. We get approximately 2/3. The top one is increased slightly, but then the bottom one, again, ignore this plus 12, we're subtracting 12 times a negative huge value. So that's a huge plus. So we're actually adding more to the 3. So the 3 is actually pretty big as well. So this 3 is bigger than what it normally is. And that contribution is bigger than plus 1. So this one is slightly below 2/3. Yes. So in terms of the bottom trend, we are approaching 2/3, but it's slightly below 2/3. I hope that makes sense. But again, if not, don't worry about it. You could probably stop here for most classes. But because these two horizontal asymptote approaches are in agreement, then we say, since these two end behaviors are pretty much in agreement, we can say horizontal asymptote is y is equal to 2/3. All right, there we go. Let's take that whole thing and plant it here. Do we have any x-intercepts? No, we don't. Because if you try to force the top to be equal to 0, we're going to get 2x squared plus 1 is equal to 0, and then 2x squared is equal to -1. Because it has no real solutions. So no x-intercept on the top. And of course, we will have a y-intercept. Right? So, wait a minute. Delete that. So we plug in 0 for x, that becomes 0, that becomes 0, that becomes 0. We get 1/12. So when x is 0, y is 1/12. And that is our y-intercept. Okay. So we have our vertical asymptote, we have our horizontal asymptote, and now we have our y-intercept. So we can get to graphing. 2/3. So x-axis, y-axis. Let me move this over. Since our vertical asymptote is at 2, there's no reason to leave so much space for the side. So I'll do this. Okay. So 1, 2, -1, -2. 3, 4, 5. Vertical asymptote is at x is equal to +1. So I'm sorry, +2. Why did I say 1? So this is VA1. That's the only VA. X is equal to +2. So we're done plotting that one, and then now we have our horizontal asymptote is at 2/3. So here is +1. Here's 2/3. Here's 1/3. So it's like here-ish. And that's the horizontal asymptote. Y is equal to 2/3. So for the x approaches a huge number that's positive, then we're slightly bigger than... Wait, did I get that in reverse? Oh, I have this in reverse. Okay. So again, if x approaches a huge positive number, then we're subtracting a bigger number from the bottom, right? Yeah, we're subtracting a bigger number from the bottom. So we're slightly below 2/3 on the top. We'll double check this afterwards. So this is like slightly below, and this is slightly above. Because I didn't put the negative right here. What am I doing? You know, let me put the negative on the top. So as x approaches a negative huge size number, it's practically 2/3. But this becomes plus extra, and this is plus extra. So the numerator, the denominator is a much greater than 3, and then the top one, I'm sorry, the denominator is slightly bigger than 3, And then the numerator is slightly bigger than 2, but this slightly bigger is bigger than this slightly bigger, which sounds kind of funny. So it's 2/3 plus. And the opposite is true for this one. As x approaches huge positive values, then it's approximately 2/3, but we're subtracting more from the bottom than we're adding to the top. So it's slightly... No. Okay. I'm sorry. Let me take that back. I was correct the first time. Okay. Backtrack just a little bit. Everything I said was correct, but the overall conclusion is wrong. So let me rephrase that again. So, as x approaches a huge size negative value, this one, we're adding more to this one. So the denominator becomes 3 big plus. And then the numerator becomes 2 slight plus. Since we're adding a tiny bit more to the 3 than we're adding to the 2, then the denominator is deviating more. So when we're dividing by a slightly bigger number, this overall is smaller than 2/3. Yes. And the opposite is true for this one. So as x approaches a huge positive value, this is approximately 2/3, but we're subtracting from the 3. So we have a 3, we're having a big subtraction, but it's still very close to 3. And then the top one is 2, we're adding slightly by 1. So since the denominator is slightly below 3, then the answer is slightly bigger than 2/3. Yes. 2/3 plus. Okay. Which allows us to determine whether or not the arrow is above or below 2/3. So when x approaches positive infinity, we are slightly above. When x approaches negative infinity, we are slightly below 2/3. There-ish. Okay. That's fun times. Now let us put the y-intercept 0, 112, which is below the horizontal asymptote. So 0, 112, here-ish. Do we have enough to graph this nonsense? Probably, right? If your suspicion is this one right here, like this one connects to here, and then trust the trajectory. This one, we have no trajectory, so we need to plug in positive 3 real quick. Okay, so we plug in positive 3, this becomes 9, 9 times 2, 18, 18 plus 1 is 19. So, plug in positive 3, we get 9 times 3, which is 27. 3 times that one is negative 36. Ooh, and then we have plus 12, okay. So we have 39 minus 36 is positive 3. So 19 over 3 is 6-ish. So 6-ish. It's like this. That seems kind of wrong, though. I would have predicted something else because of this number right here, right? So maybe we don't trust this one, right? Let's see. I don't trust this. There's something wrong with it. Okay, so again, plugging in positive 3, we're going to get positive 6-ish. So this one is probably correct. We could do an analysis to verify, but let's not do that for now. Let's check this side real quick. So if we plug in positive 1, what happens, right? So we plug in positive 1, positive 1, positive 1. Something special happens. Positive 1 comes 2. 2 plus 1 is 3. Put in positive 1, positive 1. The 2, negative 12 cancel positive 12. We're left with 3. So that's equal to 1. And that is very interesting, right? Because if that's positive 1, when we plugged in 1, we're right here. We are above the horizontal asymptote, which is in conflict. So this is where connecting those two would have led us astray, right? So let it be known that it doesn't always work. All right, so what is happening Are we crossing the horizontal asymptote yet again? And yes, that's okay. All right. And the reason why we must cross it is because if we trust this one, it has to be going upwards because this is multiplicity 2. That follows parabolic characteristic at this particular vertical asymptote. So it has to be parabola-like, upwards right there. So I have great confidence that this is correct. So we have to connect it like this. This is where things get weird, right? So if you had put this above, it would have been weird. But we put it below. So it's still a little weird because you do have to swing back around and go like this. And that should be it for the graph of h of x. So a few weird things that are happening. We have this upwards, but that should make sense in the context of even multiplicities. So this is in agreement with what we learned from polynomials, graphing regular polynomials. So upwards, yes. And then this thing is a little funky. Do we trust that it's slightly below 2/3, right? Like, is that reasoning good enough that what we did before? So let's check it real quick. So this isn't exactly a robust test, but it's good enough for us. So what if we plug in something that's very huge size negative, right? So let's plug in something like 1,000, negative 1,000, yet again. So if you plug it in, we're going to get positive 1 million times 2 is 2 million. And it's only being increased by +1. What's happening to the bottom one? Same thing. 1,000 squared is like 1 million times 3 is 3 million. So if we just had this, it would have been 2/3. But we don't have that. We have minus 1,000. I mean minus 12 times minus 1,000, which is plus 12,000. And we still have a plus 12 technically, but this is not so important. All right. So again, if we didn't have those parts, we would have 2/3, but the top portion is partially increased and the bottom portion is also increased. This increase is more sizable than this one. So as a result, we are deviating from 2/3 a little bit on the bottom and a tiny bit on the top. So the numerator deviates from 2 by a little bit, but the denominator deviates from 3 by a bit more. So we're slightly below 2/3. So yes, that's in agreement. You could crunch the numbers to verify yourself. And you'll see the same is true if you go with more zeros. All right, that's good enough. Let's analyze this portion right here, right? Do we feel confident that this is upwards if you ignore multiplicity rules, right? And we could just verify that. So we can't plug in positive 2 into our function because that fails. Because we will be divided by 0. So we plug in close to 2. So slightly below 2 and then slightly above 2. That is the idea. We don't have to do the exact plug and chug, but let's check it out. So if you plug in almost 2 in here, that's a positive number plus positive. So that's positive on the top. If you plug in slightly below 2, we get almost 0, but it's negative almost 0. Another but, it gets squared. So that's almost 0 negative squared. So that becomes almost positive. I'm sorry, it becomes truly positive almost 0 times 3. So when you take positive number divided by almost 0, that's still positive, you get positive infinity. Which is why it explodes upwards for that slightly below negative 2. But what if it's slightly above positive 2? I said negative 2, I mean positive 2. I'm getting fatigued at this point. Okay, so what if we plug in slightly above 2? Like this one, for example. Let's see what happens. Same situation. Alright. So if we plug in slightly above 2, slightly above 2 minus 2 is 0, but it's a positive looking 0. So if we square it, it's still almost 0, but it's positive. Times 3, then we don't care. And then the top portion, if we plug in this one, it's a clearly positive number plus 1. So in essence, it's a positive number on top divided by almost 0. That's positive. So that explodes positive infinity approximation. So yes, agreed. So that gives me great confidence that this answer is correct. Yes, we do cross the horizontal asymptote, which is not totally weird. Look at this funky shape right here, but that is correct. Okay. So again, disclaimer, if you didn't graph this one and you didn't know this is below and you put it above, you would have gone astray by doing this, and that would be wrong. All right. I think that's all the scenarios I want to talk about for B, for the B scenario. So let us finish off by talking about C scenario. And this is like the funkiest one. But we still have mostly the same ideas carrying over from A and B to scenario C. So again, that's when the numerator exponent, the leading term on the top, exceeds the bottom leading term by exactly 1. So let's do the easy one first. So if we have x squared minus 1 all over x. That's a fairly easy situation. Exponent 1, exponent 2. G of x. Final scenario. All right. Well, we have sub-scenarios. So when we work with this, same idea. Let's find the vertical asymptotes first. This is the easiest one. It's just 0. X is equal to 0. We'll break our function. Therefore, x can't be 0 for domain considerations. Which means we have a vertical asymptote at x is equal to 0. Yes. Now, here's the funny part. Whenever the top one exceeds the bottom one in terms of the degree, you have to use synthetic division first to simplify this, because this is an improper fraction like back in the old days. So I guess when you have like 3 over 2, for example, your teacher always told you, you got to change it to a mixed number, so 1 and 1/2. So to do that, you need to do the long division, right? So 2 into 3, you get 1. And then you get remainder 1. So 1 over 2 gets you the 1/2. And we have to do the same thing for this scenario right here. So for this one, we have to do synthetic division or long division. It doesn't matter. Synthetic division is a little faster. Synthetic division works when this is degree 1. If this had been instead degree 3 and degree 2, then you have to do modifications for your synthetic division, which I don't know how to do. So let's just do long division. So this one is x. And this one, just to practice it, so we can remember how to do it. All right. Now how do we do this? We try to match this one perfectly with this one. The perfect match would be x power 1. So x power 1 times x power 1 gives you x power 2. Subtract them. We get 0. Drop this one down. Well, we can't fit this one in there, so we have a remainder of -1. So remainder -1. But the more advanced way to do it, instead of writing remainder 1, is this. We have a remainder of -1. We tried to divide by this, but we failed, so we'll leave it as -1 over x. That's it. Okay. And since this is just a 1 term on the bottom, we could do fractional decomposition. So you could split this into x squared over x minus 1 over x. And again, this only works because the bottom is only 1 term. So you can change it like this. So therefore, 1 -1 over x, which matches, wait a minute. Oh, almost goofed up. X squared divided by x, down take the exponent, copy paste. Okay, now it matches. Yes. But don't worry about fractional decomposition just yet. You can rely on good old long division. So that's what we have. So in essence, we've changed this form from improper fraction into quote unquote proper fraction. So we get x minus 1 over x. This one still gives us the vertical asymptote. What is this one doing? This is now something referred to as the horizontal asymptote. This one right here is x. So you notice I saved the magenta for this one, right? Was it pre-planned? Yes. So slant asymptote. Slant line is a linear function. This is just a linear function. It's going to be y equals mx plus b, right? So since we just have an x, then b is value is 0 and the slope is 1. So for the slant asymptote, it's going to be y is equal to x. That's it for this one. I'll explain why in a moment. So we don't have a horizontal asymptote. We instead have a slant asymptote because the numerator exponent is greater than the denominator's leading exponent. Okay, but why is that? If we try to use this shortcut that we learned from scenario B, where you match the coefficients, you match the exponents, and then you just simply divide the coefficients. Well, we can do the same thing for this one. Do these ones match up? No. So we can force 0x cubed. And now this one matches this one. But the problem is you divide 1 by 0. What's 1 divided by 0? Positive infinity. Upwards, right? And now you're going to see why that's going to make sense. So let's go back here. Slant asymptote. I'll just show you what that looks like on the graph. And hopefully it will click. So trust me on this for now. Alright. So we have a vertical asymptote at 0. That's nothing special, nothing new there. But what the heck is this? Like I said, this is a linear function. You just have to trust me for now. So it has a slope of 1, but the x-intercept, y-intercept is at 0. So planted here, slope of 1, 1 to 1. Alright, so I told you to trust me for now, but I'll explain that in a moment. So how do we graph this situation, right? So we're going to plug in 1 point away from the vertical asymptote, which is at 0. So we plug in 1 here, so 1 minus 1 is 0. 0 over 1 is 0. So if we plug in 1, we're going to get 0. So here-ish. Okay. And then again, plug in 1 space away from the vertical asymptote in the other direction, so negative 1. So if you plug in negative 1 squared, it's positive 1. Positive 1 minus 1 is 0. 1 over negative 1 is still 0. So we're here. Which doesn't exactly help us very much, right? Because we only have 1 point. We don't know the trend situation as before. So before, when we have a horizontal asymptote, it's a lot more straightforward. Like, oh, we're hovering above it or we're hovering below it. But in this case, we don't have those guide arrows at the moment. So what do? We can check the behaviors as we get closer to this one. So now we kind of need the more robust strat. So let's check it out. So we can't plug in 0 directly into our function. We plug in something close to 0. That's even closer than 1. Why do I still have this? Whoops. Alright. Well, that little orange is going to bother me. I'm going to delete it anyway. Doesn't matter. Okay. So again, we can't plug in 0, so we're going to plug in slightly above 0. So let's see what happens. So slightly above 0 is like 0.001, right? Plug that in, we're still going to get 0. The top number will be 0-ish minus 1, which is negative 1. We plug in that in there. It's almost 0, but it's still positive. So what happens when we divide negative number by almost 0? Well, number one, the signs don't cancel. So anything divided by almost 0 explodes, so it's negative infinity. So from here, it's negative infinity. Now we have a way to connect this one to this one. If you trust the trajectory, try not to cross this, right? So why does this make sense? Why does it go upwards? So what is this exactly saying? So it has, as x changes, as x increases, y also increases. You see that? That should make sense. Because in the context of analysis right here, when you force the 0x cubed right here, we divide 1 by 0, which is undefined. But if you think about it, if it's almost 0, it explodes. We get positive infinity. Or other way to think about it is basically this one. So if you don't like that other explanation, where you're dividing by the same degrees by dividing the coefficients, you can do it by thinking about which number, quote unquote, outgrows the other one. So the most important leading term on the top is x cubed. The one on the bottom for this example is x squared. This is too small. This is too small to matter for these ones. So in essence, this one simplifies into x over 1, which is just x. So what happens when x grows larger and larger? It's infinity. There you go. All right. Same thing with the negative infinity. So as x approaches a large size negative value, these ones become minor. This becomes minor. This one's infinity with a negative. This is infinity with a negative. Because this one is squared, the negative is gone. But this one still outgrows that one. So we have a negative infinity on the top. So that is why on this other side... Oh wait, this is not the same situation. Okay. So this is not the same problem as what we were doing. So that one is its own situation, but you could extrapolate that to this one, right? So here, when x approaches positive a huge number, this is a huge number positive squared. This is a huge number. But remember, this squaring outgrows exponent 1. So this one collapses, simplifies into just x. So when you plug in positive infinity, it's positive. But when you plug in negative infinity, the square here gets rid of the negative, right? But the negative here isn't gotten rid of. So you still have a negative value. So this whole thing becomes negative infinity as x approaches a huge size negative number. All right. Wait, is that what I wanted to say? Oh yeah, that's for the long-term end behavior. Yeah, so that's right here. So that is correct, and then we could connect this one to this one, and following the trajectory, he'll be going upwards. Again, we could verify this one real quick. How do we know this one goes up? Let's check it out again. So again, we can't plug in 0 exactly because that will break our function. So we plug in something slightly less than 0, right? So if we plug in something slightly less than 0, like for example, negative 0.0001, plug it in there, it's practically 0. 0 minus 1 is a negative 1-ish, right? So if you plug in this one here, we're almost 0, but it's negative. Negative cancels with negative. So 1 divided by almost 0 is positive infinity, which verifies this one right here. So that is correct. And our graph is complete. So I hope that your trust was placed correctly. Like I said, this one is a linear function. It's a tilted asymptote called slant asymptote because our function, the top one outgrows the bottom one. So this one approaches infinity like so. It has to be going up over time. It doesn't plateau to a certain value. It grows without bounds because squaring outgrows singular x. And then in the other direction, for the same reason, essentially, the top one outgrows the bottom one because this is squared versus 1. But the signage is important because the bottom one, the negative sign, never cancels out. So that's why it grows without bounds towards negative infinity. And that's it for the slant asymptote. And I'm just going to go over one more example with the slant asymptote. And because I'm getting tired. All right, let's see. And this is just a tutorial. We're going to be doing problems in the next meetup. All right. So again, when the exponent is exactly greater than the bottom one by 1. And you'll always be given nice problems. You're not going to be given something that's not factorizable. At least from my experience. Alright, so let's do something a little more complicated. So we're going to have x squared minus 3x minus 4 on the top. Now let's do plus 2. Yeah. And then the bottom portion, I'm just recycling the same situations, right? That's kind of on purpose. Alright, on the bottom portion, we're going to get x squared minus 9. So difference of two squares. Exponent on top is... Oh, this is not the right situation. We need the top to be greater than... I'm sorry. Let me change the top one. So let me just multiply the top by x, and that'll make things much easier. So x cubed on the top, 3x squared right there, and then 2x. Okay. Otherwise, we won't have scenario C. There we go. All right. First, I always like to open up with horizontal asymptotes. So what are... Oh, we got to factorize. I'm sorry. I'm getting tired, you see. So factorize the top one. We could factor out x from each term. So it becomes x times. Becomes x times x squared minus 3x plus 2. This one is further factorizable. Just follow your favorite algorithm. Minus 2 minus 1. Alright, that's the numerator. Denominators are just a difference of two squares. Use your favorite factoring algorithm, please. Alright. So there we go, fully factored form on top and on the bottom. So let's deal with the domain issues first. So if x is equal to negative 3, we create 0. If x is equal to positive 3, we also create 0. So therefore, for the domain, x cannot be negative 3 nor positive 3. Which means we have two vertical asymptotes. So vertical asymptote number 1, x is equal to negative 3. And then vertical asymptote number 2, x is equal to positive 3. Alright. Done with that nonsense. Now we deal with horizontal asymptote. Just kidding. Because this one is 1 greater than this one. So we have to use long division, unfortunately. Technically, you could use synthetic division tool. No, you can't. It's weird. It leads to... I don't know how to do it. I think there's a way to do synthetic division. But I don't know how to do it with degrees greater than 1. So I'm going to do long division. Sorry. So we have x minus 9 into this one. kind of tedious, but not very difficult. All right. So this is written kind of weirdly. This is written very weirdly. All right, hold on. Okay. So how do we get this to perfectly match this one? As long as we get x powered 1. So x times this one, we subtract it from what's inside. We already went over long division some time ago. So this one times this one. This one times that one. Oh, I should have included this. I'm sorry. Let's include that. All right, so here's what I realized, right? Because this one times this one yields minus 9, it is applicable to this one. So we should drop this one. So I'm going to put the parentheticals way right here. So again, this one times this one gives us negative 9x. That feels weird. Something feels really off. Okay, that's fine. So doing the subtraction, this one cancels with this one perfectly. That's what we wanted. This one has nothing to subtract, so we just drop it straight down. That feels really weird. And then we have this one minus minus, so it's going to be plus 11x. Okay, that's fine. Next up, how do we get this to perfectly match that one? It's negative 3. All right. Minus. This one times this one. This one times that one. Perform the subtraction, so this one perfectly cancels with that one. Drop that one straight down. That's technically negative, so negative 27. So thus, we have a remainder of 11x minus 27, which again, put it in fancy mode, it's plus 11x minus 27. We failed to divide it by x squared minus 9. So this is a restated version of this one. And we did that so we can get this thing right here. That's not the horizontal asymptote, that is the slant asymptote. It's a linear function, y equals mx plus b. Alright, so let us put that down. So slant asymptote is therefore, we need to write it as a linear function, y is equal to mx plus b. There it is. So I'm going to take that and move it over. We still have a few more things to go. What do we have at this point? Okay. We have x-intercepts, of course. We have x-intercept 1, x-intercept 2, and x-intercept number 3. So let's solve for each of those. So x is equal to 0. That's the first 0 on top. And then the second 0. Third 0. So x-intercepts, remember to put them in point form. So 0, comma 0. 1, comma 0. 2, comma 0. And we should have enough to start graphing stuff. Oh, let's find the y-intercept. So y-intercept when all the x's are 0, so this is 0, 0, 0, 0. So we have 0 over negative 9, which is just 0. So these are the same thing. All right. Well, I should have known because we have a 0 here, and that's 0. That's wasted effort. That's okay. Let's get to graphing. What do we have? We have 2 vertical asymptotes, and then we have a slant asymptote that's a little lower. All right. So I want to put the x-axis a little bit higher. So we have two vertical asymptotes. -3, +3. Then put hash marks. Feels weird not putting more hash marks. Let me put more. Alright. So that looks good. VA1. And that's occurring at x equal to -3, and then VA2 is at +3. Cool. Next we have slant asymptote at y is equal to x minus 3. So find -3. 1, 2, 3. Here. Slope of 1, so rise of 1, run 1. Ooh, it's going to cut off. That's okay. I put it a little too low. Rise of 1, 1, 1. So this is 1, 2, 3. 1, 2, 3 here. Okay. So that looks a little funny, right? So how do we graph this nonsense? Oh, we're going to put the x-intercept and y-intercepts. So y-intercept at 0, 0. 1, 0. 2, 0. Y-intercept at 0, 0. Well, that's really weird. That's really weird. What is it doing? Okay, well, that's interesting. Okay, so moving forwards, we now deal with color orange to figure out what the graph is going to look like. So we're just going to plug in one space away from each vertical asymptote in both directions. So we're going to plug in -4 and -2. -4 and -2. See what happens. Oh, that's annoying. -4, -2. No point. Okay, -4. And -4. This is why we plug in one space away, because we get -1 on the bottom there. -4. Okay, we have negative on top, positive on bottom. This is 30 times 4 is 120, and the bottom one is 7. So that's a huge negative number. That's all we care about. Okay. So plugging in -4, we get a huge negative number somewhere down here. So our graph is going to be something like this. Because we can't break past the vertical asymptote ever. Long-term end behavior, that's fine. We're approaching -infinity. So as x approaches, this is for end behavior, remember. As x approaches -infinity, then y value approaches. According to our graphical prediction, we're saying that y approaches -infinity as well. Let's see. This one outgrows this one. So if you simplify this, that becomes x power 1. Yes. So if you plug in -infinity, -infinity. There you go. So we have great confidence that this is correct, and this should be correct. All right. So that's it for that part, and then next we have to plug in -2 to figure out what's happening here-ish. So let's see. Let's clear this. All right. So if we plug in, what if we plug in? -2, right? -2. -3. -4. That's why we plug in -2. -5. So what do we get? We have an even amount of negative, so the negatives will have canceled out. So 2 times 3 times 4, which is 24 over 5. Again, all these negatives have canceled out. All right. So we have close to positive 5 for the situation. Almost positive 5. So it's like up here-ish. Okay, so we're probably doing something like this. But how do we reconcile this situation, right? In essence, this is like a polynomial. Right? In actuality, it is a polynomial, right? So if we set it equal to 0, then it should be behaving like a polynomial like that one, right? Oh, it's odd. Let me think. But we have to divide. So it becomes even powered, right? Yes. So I think it's going to be doing... that's weird. Okay. What will it be doing? Like this, like this, like this? Okay, that's kind of weird, right? Well, I'm going to ignore this for now. We'll come back to this. Because it is a little strange. Yeah, we'll come back to what's happening between those ones. We're fairly certain it's going to do something like this. But what's happening right here, right? And will we be crossing the x-axis? That is the question. So... yeah. Okay, so what I'm going to do, you can plug in, we can't plug in one space away from this vertical asymptote because we already have it right here. So you can plug in half a space away just to see what happens. So we could do it like that. Let's do that. So this is 3, so we're going to plug in 2.5. So if we plug in 2.5, what do we get? We get 2.5. We get 1.5. And we get a very unpleasant negative 0.5. Wonderful. No, yeah, that's correct. Because we're plugging in 2.5. Plug in 2.5 here. Very unpleasant. 2.5 there. We get a negative value as well. Wait. Huh. Am I confused? Oh, this is positive. I'm sorry. This is positive. Yeah, okay, yeah, that's positive. Thank goodness. This is negative 0.5. Yes. So this cancels with this, but our signages don't cancel. We have to put a negative in front. What does that mean for us? This one times this one. What does that give us? I think that's below 5, right? Because 3 times 2 is 6. So, I'm actually going to resort to a calculator because my brain is frazzled at this point. So 2.5 times 1.5 on the calculator gives us 3.75. Yes. Negative over 5.5. So we can see that this is a negative value that is below. It's a negative value, so it's below x-axis. That's very interesting, right? So plugging in 2.5, positive 2.5, we got negative value. So plugging in 2.5, we got a negative value, which is what? Which is above negative 1. So here is negative 1, so we are above negative 1. So this is where the drawing is kind of poor, right? So are we here or are we there? So that's a little ambiguous. Okay, so we have to use the more robust method to figure out what is our behavior as we get close to 3. Okay, so this was a waste of time, in my opinion. All right. So again, we can't plug in 3 directly into our function. It will break our function. So we plug in something slightly close to that. We plug in something very close to 3 that's slightly below it. So 2.999 is the idea. Okay. So if we plug that in, what happens? We get close to 3. We get close to 2. We get close to 1. Plug it here, we get close to 6. here's where the thing is interesting. Almost 3 minus 3, but it is slightly below 3. So we have a 0, but it's almost 0, but it's still negative. All right. So we have positive value on the top. We have almost 0 on the bottom, but it's negative. So this is negative infinity. Yes. So we actually explode downwards. Perfect. All right, so this is where the points are very funky, right? So that means that I think it does something like this. That looks really, really weird. But I think that is correct. Okay, so that's just a weird situation. So this part is probably basic like that one. So let's test positive 4. Okay, plug in positive 4, right? So we get 4, 3, 2, positive 4 is 7, positive 4 is 1. All right, perfect. So we're going to get 24 over 7, which is above 3. So it's 3 and 3/7. So close to 3.5. Close to 3.5. So here-ish. Okay, so as predicted, it ends up right here. So we're probably doing something like this. And that should make sense, because this factor is a multiplicity of 1. So we should have that alternating situation, yes. And this one should make sense as well. Understanding the, as x approaches positive infinity, what happens to our y values? This one outpaces this one. So we can simplify this to just x over 1. So when you plug in positive, a huge positive number, it becomes a huge positive number. So y value approaches huge positive number, yes. So this one makes sense. So that is how we graph this situation, and we are done with that one. Let me check the calculator real quick, because I think this part is really funky. So I want to verify that. So I'm going to cheat and plug it into my calculator. Let's see. On the top, we have x times x minus 1 times x minus 2. Close parentheses all over x plus 3 times x plus 3. I mean minus 3. Close parentheses. Let's hit input. What do we get? Yeah, it agrees. Okay, it's good. Yeah, it's doing the funky things. I probably exaggerated a little bit too much, honestly. So right here, I think it's better if you just do less bumps, like this, something like this. So if we were to make this a little better, it would be like this, like a little bit of bump, a little bit of bump, and goes down. As you see, we crossed the slant asymptote just like how we crossed the horizontal asymptote before. Remember, long-term behaviors are summarized by horizontal asymptotes, not local behaviors. But we can never cross vertical asymptotes. Okay, I'm pretty satisfied with this one. We are done with that one. But there's actually one more thing I want to go over. Let me think. You know what? No. I think I'm going to call it. I was going to go over the concept of holes, but I'm going to save that for next time. But let me write that down right here. So we're basically done with the situation, but there are something called holes. So that's basically when your graph does something like this. And there's a whoop, there's nothing there. We'll talk about that next time, because I'm really tired at this point. Alright, so with that said, I think we are good to go. I know that was a tremendously long time for a tutorial, but you know, I'll put up the timestamps as usual so you can click to your heart's desires. There were some mishaps, but that's what we get with going live, right? Okay. Other than that, I'm done for today. I hope you have a good one, and I'll see you in the next one.